There are asteroids in space spinning so fast that, by all logic, they should have torn themselves apart long ago. But they haven't. They defy physics, orbiting the sun at breakneck speeds, challenging everything we know about gravity and motion. How do they stay intact? Are they held together by some unknown force? Or are we missing something fundamental about how space works? Scientists are only beginning to unravel the mystery, and what they've discovered so far is nothing short of mind-blowing. But before we continue, subscribe to the channel so you don't miss out on any of these videos. Ultra-rapidly spinning asteroids are one of the strangest mysteries in our solar system. These asteroids complete full rotations in just seconds or minutes, while most others take hours. Scientists have found asteroids spinning so fast that they should theoretically be unable to hold themselves together. If you imagine a spinning top, at some point, it wobbles and falls over. But these asteroids don't stop. They keep spinning, faster and faster, beyond what physics suggests should be possible. How are they doing this? Could there be hidden forces we haven't yet discovered? Asteroids, in general, are remnants of the early solar system, leftovers from when planets were forming. They come in all shapes and sizes, tumbling through space, colliding, and breaking apart. But ultra-rapidly spinning asteroids stand out because they break a fundamental rule. Most loose rocks held together only by gravity can't spin beyond a certain speed, or they'd disintegrate. Yet, we see these asteroids doing exactly that. Are they made of something different? Do they have some internal structure that keeps them from flying apart? One theory suggests that these asteroids might be monolithic, meaning they're solid chunks of rock rather than rubble piles held together by gravity. If they were solid, that would explain their ability to spin rapidly without breaking apart. However, that creates another mystery. How did they stay intact after billions of years of space collisions? Another theory suggests they might be experiencing a force called the YRP effect, where sunlight unevenly heats the surface and causes them to spin faster over time. But can light alone push an asteroid to spin at such extreme speeds? Astronomers have detected dozens of these ultra-rapidly spinning asteroids, and the more we study them, the more questions arise. Some are small, just a few meters wide, while others are larger, yet they all share one thing in common: they shouldn't be spinning as fast as they are. Some of them complete a full rotation in less than a minute. To put that in perspective, imagine Earth spinning that fast. A single day would last less than 60 seconds. The forces at play would tear everything apart. The YRP effect, named after the scientists who discovered it, suggests that sunlight exerts tiny but continuous pressure on an asteroid's surface. Over millions of years, this small push builds up, increasing the rotation speed. But there's a problem. This effect works gradually. For an asteroid to spin as fast as some of these ultra-rapid spinners, it would need a massive amount of sunlight exposure over billions of years. Some of these asteroids are too young for that explanation to make sense. So what else could be going on? Some astronomers suspect that collisions play a role. If a smaller rock smashes into an asteroid at the right angle, it could transfer energy and make the asteroid spin faster. But that still doesn't fully explain why some of these asteroids have reached extreme speeds. Another possibility is that they were once part of larger objects and were ejected from a high-speed impact, carrying the rotation with them. If that's the case, studying them could give us clues about ancient cosmic collisions. One particularly strange asteroid, known as 2017 QG18, spins so fast that scientists initially thought their data was wrong. It completes a full rotation in just over 10 seconds. That means any loose material on its surface should have been thrown off long ago. But it remains intact. Could there be some kind of unknown bonding force keeping it together? Some researchers suggest that electrostatic forces, similar to the way dust clings to a screen, might help hold the asteroid's surface together despite its extreme speed. But if that's true, then what other effects could these forces have across the cosmos? Then there's the question of whether these asteroids are a recent phenomenon, or if they've always been this way. Are they part of a natural cycle where asteroids gradually spin faster until they break apart? Or are we witnessing a phase in their evolution that's only temporary? If they do eventually shatter, what happens to the fragments? Could ultra-rapidly spinning asteroids be the source of smaller meteoroids that rain down on planets like Earth? Even more baffling is the idea that some of these asteroids might be hiding clues about the origins of our solar system. If they have remained unchanged for billions of years while spinning at extreme speeds, what does that say about their composition? Could they contain pristine materials from the birth of our solar system, untouched by the usual space weathering? There's another possibility that some researchers hesitate to discuss. What if some external force is acting on these asteroids? Could an unknown cosmic phenomenon be influencing their rotation speeds? The universe is full of strange, unexplained forces. We already know that dark matter, an invisible substance making up most of the universe's mass, affects the motion of galaxies. Could something similar be affecting these asteroids? And here's another weird question. Could these asteroids be artificial? It sounds like science fiction, but the idea has been brought up by serious researchers. If an object were built to spin at extreme speeds, it could theoretically serve as a kind of space probe or beacon. While there's no direct evidence for this, it's a question that arises when something behaves so differently from everything else in space. As we continue to track these asteroids, scientists hope to uncover more about their nature. Future space missions might even attempt to visit one of these ultra-rapidly spinning asteroids to take direct measurements. If we could land a probe on one, we could finally determine what they're made of and whether they contain internal reinforcements that allow them to withstand their extreme rotation speeds. For now, these asteroids remain one of space's strangest mysteries. Are they simply the result of natural forces acting over time? Or do they hold secrets that could change our understanding of the universe? The more we study ultra-rapidly spinning asteroids, the more bizarre they seem. If they were ordinary space rocks, they should have broken apart long ago. And yet they persist, defying our expectations. Some researchers believe that these asteroids could be shedding material in ways we haven't yet observed. If an asteroid spins fast enough, it might gradually lose layers of dust and rock over time, making it seem as though it's surviving when, in reality, it's slowly falling apart. But if that's true, why haven't we detected these fragments floating nearby? Could they be dispersing in ways we don't understand? One possibility is that these asteroids might be held together by forces beyond just gravity. When we think about asteroids, we often picture them as solid chunks of rock, but many are actually loose collections of rubble, barely clinging together. If an ultra-rapidly spinning asteroid were a rubble pile, it should fling itself apart almost instantly. But some scientists suggest that these asteroids might have tiny forces, like van der Waals forces, weak molecular attractions, keeping their particles together. If true, that would mean space isn't just governed by gravity and inertia, but also by invisible forces that can operate even on large scales. Another possibility is that some of these asteroids might contain frozen materials, like ice or other volatile compounds, that evaporate when exposed to sunlight. If gas is being released, it could create a tiny amount of thrust, pushing the asteroid to spin faster over time. This would mean that ultra-rapidly spinning asteroids aren't just unusual. They could be active objects, constantly changing as they move through space. If some of them contain water ice, it could even mean that they played a role in delivering water to Earth billions of years ago. Scientists have also considered whether these asteroids might have magnetic properties affecting their spin. Some meteorites that fall to Earth contain high amounts of iron and nickel, and if an asteroid has a strong enough magnetic field, interactions with the solar wind could generate tiny forces that influence its rotation. This idea is still speculative, but if confirmed, it could reveal a new way in which space objects interact with their environment. One of the strangest things about ultra-rapidly spinning asteroids is that some of them seem to be accelerating. Normally, an asteroid's spin should remain stable or gradually slow down over millions of years due to tidal forces and collisions. But in some cases, astronomers have observed small but measurable increases in spin rate. This raises an unsettling question. Are these asteroids being affected by something we haven't discovered yet? Could there be an unknown force in deep space influencing their motion? Some researchers believe that these asteroids could be remnants of much larger bodies that were destroyed in ancient cosmic impacts. If an asteroid was ejected from a massive collision, it might have retained some of the original momentum, spinning faster than most space rocks. But if that were the case, we should see more of these objects, not just a handful. Could they be survivors of an era when the solar system was far more chaotic, and only the most resilient objects remained? A particularly fascinating case is asteroid 2001 OE84, which has one of the fastest spin rates ever recorded. This asteroid completes a full rotation in just over 30 seconds. That's faster than any natural satellite or planet we know of. For comparison, Earth takes 24 hours to complete one rotation. If Earth were spinning as fast as 2001 OE84, a single day would last less than a minute. The centrifugal force would be so extreme that nothing could stay on the surface. So how does this asteroid maintain its structure? Is it denser than expected? Does it have an unknown internal structure that keeps it from tearing itself apart? Astronomers are planning more detailed observations of these asteroids, but there's a problem: many of them are incredibly small. Some are no bigger than a car, making them hard to detect and even harder to study. They move rapidly, and since they don't reflect much sunlight, they can disappear from view before scientists can gather enough data. This raises another possibility. What if there are many more of these asteroids than we realize? Could space be filled with countless ultra-fast spinning objects that we simply haven't found yet? One of the biggest mysteries surrounding these asteroids is whether they will eventually slow down or keep spinning indefinitely. If an asteroid continues accelerating, there must be a limit before it disintegrates. But what if that limit is much higher than we thought? Some scientists speculate that, under the right conditions, an asteroid could spin at an extreme rate for billions of years without breaking apart. If true, that could challenge our understanding of how asteroids evolve over time. There's also an interesting question about whether these objects could be used for future space exploration. If an asteroid is spinning rapidly, could we harness that energy? Some have suggested that if we could land on one of these objects and attach equipment, we might be able to generate artificial gravity by using the asteroid's spin. While this idea is still theoretical, it raises fascinating possibilities for the future of deep space travel. Another mind-bending idea is that some of these asteroids could be fragments of ancient space structures. This is purely speculative, but there are researchers who wonder if some of the strange objects we detect in space could be remnants of past civilizations, either from Earth or elsewhere in the universe. If an ancient space station or spacecraft broke apart, could some of its pieces end up spinning like these asteroids? While there's no direct evidence for this, the fact that these asteroids behave so strangely leaves room for some wild possibilities. Ultra-rapidly spinning asteroids remain one of the most perplexing mysteries of space. As our telescopes and detection methods improve, we may start finding more of them, or even stranger objects that challenge our understanding of physics. Could they be natural anomalies, or are they a clue to forces in the universe that we have yet to discover? The deeper we dive into the mystery of ultra-rapidly spinning asteroids, the more questions arise. These objects shouldn't exist according to our current understanding of physics, yet they do. If they were like typical rubble pile asteroids, the forces acting upon them should have torn them apart long ago. And if they were solid monoliths, their existence would challenge what we know about how asteroids form and survive in the chaotic environment of space. So what's really keeping them together? One theory gaining traction is that these asteroids may contain materials that are stronger than we initially thought. Most asteroids are composed of rock and metal, but if some of these fast-spinning objects contain dense, interlocked crystalline structures, they might be able to withstand extreme centrifugal forces. Imagine a diamond-shaped asteroid made from tightly packed, unbreakable minerals. If such an object exists, it could maintain its integrity even when spinning at speeds that would shatter ordinary rock. But where would such an asteroid come from? Some researchers speculate that these ultra-fast spinners might be fragments of larger celestial bodies that once had extreme internal pressures. When these parent bodies were destroyed in ancient cosmic collisions, their most resilient fragments, pieces containing high-density materials, were flung into space. Over billions of years, these fragments continued spinning, unaffected by external forces. If this is the case, then ultra-rapidly spinning asteroids may be the last surviving remnants of planets, or planetary cores that were obliterated in the distant past. Another possible explanation is that these asteroids are in a constant state of shedding material, which might be keeping them from reaching the breaking point. If an asteroid rotates too fast, its surface material should theoretically fly off due to centrifugal forces. But what if this is happening so gradually that we don't easily notice it? If a high-speed asteroid is constantly losing dust and tiny rock fragments, it could be shedding just enough weight to keep itself intact. This would mean that instead of breaking apart all at once, these asteroids might be eroding over time, slowly losing mass but never quite reaching the point of complete destruction. This raises an intriguing question: what happens to the material these asteroids shed? If they are constantly releasing tiny particles into space, those fragments could be contributing to the formation of meteoroid streams, potentially leading to meteor showers on planets like Earth. Could some of the shooting stars we see in the night sky actually be pieces of ultra-rapidly spinning asteroids that have gradually been thrown off into space? If so, studying these asteroids might help us trace the origins of certain meteor showers and even provide insight into the composition of space dust that rains down on Earth every day. One of the strangest aspects of ultra-rapidly spinning asteroids is their apparent randomness. Some are tiny, just a few meters wide, while others are much larger. Some are found in the asteroid belt, while others exist as near-Earth objects or in distant regions of the solar system. There seems to be no single rule governing where these asteroids appear or what size they must be to survive extreme spin rates. This suggests that the factors influencing their rotation speeds are more complex than we initially thought. The YRP effect remains one of the leading explanations for why some asteroids start spinning so fast. But for the YRP effect to work, an asteroid must have an irregular shape so that sunlight can hit different areas unevenly, gradually increasing its spin over time. However, some of the fastest spinning asteroids don't seem to fit this model. They are more spherical or symmetrical than they should be if the YRP effect was the primary cause of their rotation. Could there be an additional force at play? There's also the question of whether ultra-rapidly spinning asteroids are a relatively new phenomenon. Are we witnessing them at a unique moment in their evolution, or have they always been this way? If they have existed for billions of years, they must have some mechanism preventing them from breaking apart. If they are a recent development, then what triggered their sudden acceleration? Could it be related to changes in the solar system's environment, such as shifts in gravitational influences from planets or increased solar radiation? Some researchers have even suggested that certain ultra-fast spinners could be evidence of past tidal interactions with planets. If an asteroid passed close enough to a large planet like Jupiter, its gravitational forces could have stretched the asteroid, influencing its spin. While tidal forces usually slow down celestial bodies over time, in some cases, they might actually impart rotational energy, making the asteroid spin even faster than before. If this happened millions of years ago, the asteroid could still be carrying that momentum today. One of the most mind-bending possibilities is that some of these objects could have been artificially manipulated in some way. While there's no concrete evidence to suggest these asteroids are anything but natural, the idea that an advanced civilization, either from our own distant past or from elsewhere in the universe, could have experimented with spinning objects in space is a fascinating one. If someone wanted to create a rapidly rotating object for a scientific or technological purpose, how would they do it? Could some of these asteroids have been modified or used as tools in ways we don't yet understand? The problem with studying ultra-rapidly spinning asteroids is that they are difficult to observe in detail. Since many of them are small and move unpredictably, tracking them requires precise measurements over long periods. Space telescopes like the Hubble Space Telescope and upcoming missions like the James Webb Space Telescope might provide more data. But to truly understand these asteroids, we would need to send spacecraft to observe them up close. Some scientists have proposed missions that could visit one of these asteroids, deploy small probes, and take direct measurements of their composition and structure. If we could land a spacecraft on one of these fast-spinning objects, we might finally determine whether they are solid monoliths, rubble piles held together by mysterious forces, or something even stranger. Until then, ultra-rapidly spinning asteroids remain one of space's greatest mysteries. Are they rare, Or have we only scratched the surface of how common they really are? Do they hold the key to understanding new physical forces? Or are they simply the result of chaotic cosmic interactions? As technology advances and we continue to explore the solar system, we may finally get the answers. But for now, they remain enigmatic objects, spinning faster than we ever thought possible, daring us to uncover their secrets. If ultra-rapidly spinning asteroids are as common as some researchers suspect, why haven't we found more of them? One reason is that they are incredibly difficult to detect. Many of them are small, reflecting very little sunlight, making them nearly invisible against the vast darkness of space. Others spin so fast that they don't stay in one place long enough for telescopes to get a good look at them. Unlike planets, which follow predictable orbits, some of these asteroids have chaotic trajectories, changing speed and direction in ways that are hard to track. This means that, for every ultra-fast spinning asteroid we've discovered, there could be dozens, or even hundreds, lurking undetected in the shadows. Another issue is that many of these asteroids might be in orbits that make them hard to study. If an asteroid is in the asteroid belt, we can observe it repeatedly as it follows its path around the Sun. But if it's a near-Earth object or a visitor from the outer solar system, we may only get one brief glimpse before it disappears forever. Some of these asteroids might even be interstellar objects, coming from other star systems entirely. If that's the case, they may be carrying secrets about the formation of planets and moons beyond our solar system. What makes ultra-rapidly spinning asteroids even more intriguing is that they don't all behave the same way. Some are spinning along a single axis, like a basketball rolling on a flat surface. Others are tumbling chaotically, changing direction unpredictably as they move through space. This suggests that some of these asteroids may have had violent pasts. Perhaps they were hit by other objects, causing them to spin out of control. If that's true, they might contain valuable clues about the history of our solar system, showing us how collisions and impacts have shaped the planets and moons we see today. One possibility scientists are investigating is whether ultra-rapidly spinning asteroids could be responsible for some of the unexplained high-energy impacts we've detected on Earth. While most meteorites that reach our planet come from relatively slow-moving asteroids, there have been rare cases where impact craters suggest objects moving at extreme speeds. Could some of these craters be the result of ultra-fast spinning asteroids that somehow made their way toward Earth? If so, it would mean that these objects aren't just a distant mystery, they could pose a real threat. But what if we could use these spinning asteroids instead of fearing them? Some scientists believe that if we could harness the energy of a rapidly spinning asteroid, it could become a valuable resource for space exploration. Imagine landing a spacecraft on an asteroid that completes a full rotation every few seconds. If we could attach a tether or a mechanical arm to it, we might be able to generate energy using the asteroid's spin. This could provide a new way to power future space missions, reducing our reliance on traditional fuel sources. There's also the question of whether these asteroids could serve as natural launch pads for deep space missions. If we could find a way to attach equipment to a fast-spinning asteroid, we might be able to use its rotation to fling small probes into space at high speeds. This could allow us to send scientific instruments to distant locations without needing massive rockets or expensive propulsion systems. While this idea is still in the early stages of discussion, it raises some fascinating possibilities for the future of space exploration. One of the most exciting developments in the study of ultra-rapidly spinning asteroids is the possibility of sending a dedicated space probe to observe one up close. While past missions like OSIRIS-RX and Hayabusa-2 have visited asteroids, they focused on slower rotating objects. A new mission designed specifically to study a fast-spinning asteroid could revolutionize our understanding of these strange objects. If we could send a probe equipped with high-speed cameras and advanced sensors, we might finally unlock the secrets of how these asteroids form, why they spin so fast, and what forces are keeping them intact. Some researchers believe that the key to understanding these asteroids lies in studying their surface features. If an asteroid is spinning rapidly, we would expect to see evidence of stress fractures, landslides, or even material being ejected into space. But so far, observations have shown that many of these asteroids appear surprisingly smooth. This raises an intriguing question. Are these asteroids covered in a layer of fine dust or regolith that hides their true structure? If so, could that dust be helping to hold them together, acting like a natural glue that prevents them from breaking apart? Another bizarre possibility is that some of these asteroids might be hollow. If an asteroid is mostly empty space inside, it could theoretically spin much faster than a solid object without breaking apart. This idea is controversial, but if true, it could mean that some ultra-rapidly spinning asteroids are unlike anything we've ever encountered. Could they be remnants of ancient planetary cores that were stripped of their outer layers? Could they be the husks of long-dead comets that have lost all their ice, leaving behind only a fragile shell? Then there's the question of whether ultra-rapidly spinning asteroids could be interacting with dark matter in some unknown way. Dark matter is one of the greatest mysteries in physics. It makes up most of the universe's mass, yet we can't see or directly detect it. Some scientists have speculated that if an asteroid were dense enough or moving fast enough, it might experience subtle interactions with dark matter particles. While this idea is purely hypothetical, it raises the tantalizing possibility that these asteroids could help us learn more about the fundamental forces shaping the cosmos. Another possibility is that ultra-rapidly spinning asteroids are linked to the strange phenomenon of spacequakes, seismic events that occur on celestial bodies without an obvious cause. If a fast-spinning asteroid experiences internal shifts due to its rapid rotation, it could produce vibrations similar to an earthquake. But since asteroids don't have tectonic plates like Earth, these quakes would have to be caused by something else. Could they be the result of stress building up over time? Could they be signs that some of these asteroids are slowly tearing themselves apart? Some astronomers believe that these asteroids might eventually slow down due to the effects of space dust and solar radiation. Over millions of years, tiny particles colliding with the asteroid's surface could gradually reduce its spin, much like how friction slows down a spinning top. But if that's the case, why haven't we found more examples of ultra-fast spinners that are in the process of slowing down? Could it be that these asteroids are constantly being recharged by unknown forces, keeping them spinning at extreme speeds? The search for answers continues, and as technology advances, we may finally get the chance to study these asteroids in ways that were previously impossible. Future missions could deploy robotic landers, drilling into the surface of a fast-spinning asteroid to analyze its internal structure. Advanced telescopes could detect even fainter objects, revealing just how many of these asteroids are out there. And new simulations could help us understand what happens when an asteroid reaches the theoretical limits of how fast it can spin. But for now, ultra-rapidly spinning asteroids remain one of the strangest and most perplexing mysteries of space. They challenge everything we thought we knew about how objects behave in the vacuum of space. They defy expectations, spinning faster than they should, resisting the forces that should tear them apart. Are they rare cosmic oddities, or are they the key to unlocking a deeper understanding of the universe? Until we find out, there will continue to be some of the most enigmatic objects in the cosmos, silently spinning in the darkness, waiting for us to uncover their secrets. The mystery of ultra-rapidly spinning asteroids doesn't just challenge our understanding of physics, it also forces us to rethink how space debris behaves on a fundamental level. These asteroids shouldn't exist, at least not in the way we currently understand. The laws of physics suggest that once an asteroid reaches a certain rotational speed, the centrifugal forces should overwhelm its structural integrity, tearing it apart. Yet, time and time again, we find these hyperspinning objects that remain intact. This raises a huge question: what unknown forces or mechanisms are allowing these asteroids to resist self-destruction? One of the leading theories is that these asteroids are made of a material far stronger than anything we've accounted for. Most asteroids are thought to be loose rubble piles held together by gravity and weak cohesive forces. But what if some of these fast-spinning asteroids are composed of an ultra-dense, ultra-strong material that allows them to withstand these extreme forces? Could they contain elements or compounds that are rare or even unknown to us? If so, studying them could provide insight into exotic materials that might exist elsewhere in the universe. Another possibility is that these asteroids are not entirely solid at all but instead have internal mechanisms that redistribute their mass in a way that prevents them from breaking apart. Imagine a spinning top that has weights shifting inside it to maintain its balance. Some researchers speculate that if these asteroids contain loose material inside, their rapid rotation could cause the internal mass to redistribute in a way that stabilizes them rather than tearing them apart. This would mean that these asteroids are behaving more like dynamic, self-regulating systems rather than simple, rigid objects. But even if these internal mechanisms exist, there's still the issue of how these asteroids achieved such high rotation speeds in the first place. Some scientists believe that the Yarkovsky-Oki-Fradzievsky Paddock (YORP) effect could be responsible. The YORP effect is a phenomenon where sunlight heats one side of an asteroid, causing it to emit infrared radiation in a way that generates a tiny amount of thrust. Over millions of years, this constant but gradual force could cause an asteroid's spin rate to increase. However, there's a problem with this theory. If the YORP effect were solely responsible for accelerating these asteroids to ultra-fast speeds, we would expect to see a gradual progression of spin rates across different asteroids. But instead, what we see is a puzzling pattern. Some asteroids rotate at moderate speeds, while others spin at extreme rates, with very few in between. This suggests that another mechanism, perhaps an unknown one, is playing a role in accelerating these objects. Some astronomers have proposed that these asteroids may have had violent pasts involving close encounters with massive planets like Jupiter or Saturn. If a small asteroid passed too close to one of these gas giants, the immense gravitational forces could have acted as a slingshot, imparting extreme rotational energy. This could explain why some of these asteroids spin so fast, but it still doesn't explain why they haven't shattered into pieces. Another wild theory suggests that some of these asteroids might have originated from outside our solar system. If an asteroid were ejected from another star system due to gravitational interactions, it could enter our solar system at extreme speeds, already spinning rapidly due to forces we don't fully understand. If this is the case, then some of these ultra-rapidly spinning asteroids might not just be space rocks. They could be interstellar messengers, carrying material from alien star systems. And then, of course, there's the question of whether some of these objects could be artificial in origin. While this is a highly controversial idea, some researchers have speculated that ultra-fast spinning asteroids could be remnants of ancient alien technology, perhaps derelict spacecraft or probes that have been drifting through space for millennia. If an advanced civilization sent out exploratory probes long ago, it's possible that some of them could have become coated in dust and debris over time, making them look like natural asteroids. The rapid spinning could then be the result of an internal mechanism still functioning in some way, even after eons in space. One of the biggest challenges in studying these asteroids is simply getting close enough to observe them properly. Most telescopes can only detect these objects as tiny, fast-moving dots against the backdrop of space. The best way to truly understand them would be to send a space probe equipped with high-speed cameras and specialized instruments capable of analyzing their composition, rotation, and internal structure. However, landing a probe on an asteroid spinning at extreme speeds would be an engineering challenge unlike anything attempted before. Imagine trying to land a spacecraft on an object that completes a full rotation every few seconds. Any attempt to touch down would be met with enormous centrifugal forces, potentially flinging the spacecraft away before it could establish a foothold. Even if a probe were able to attach itself, the constant motion could make it nearly impossible to conduct detailed scientific experiments. One possible solution would be to send a probe that doesn't land but instead orbits the asteroid at close range. By flying alongside it, and using advanced imaging techniques, scientists could create high-resolution maps of the asteroid's surface, identify weak points, and look for any signs of unusual activity. A probe could also deploy tiny robotic drones capable of making brief contact with the surface, gathering samples before being ejected back into space. But even with all these technological advancements, studying ultra-rapidly spinning asteroids remains a daunting task. The biggest challenge is time. These objects are constantly moving, and many of them may only be visible for a short period before they vanish into the depths of space. Some may never return, making every observation a once-in-a-lifetime opportunity. Despite these difficulties, the scientific community remains eager to unlock the secrets of these strange asteroids. Understanding them could provide insights into how planets and moons form, how celestial objects evolve over time, and even how life might spread throughout the universe. If we can determine why some asteroids spin so fast without breaking apart, we might also gain new knowledge about material strength, structural integrity, and the fundamental forces governing space. There's also the potential for practical applications. If we learn how these asteroids maintain their structure under extreme rotational stress, it could lead to new materials and engineering techniques that benefit future space missions. The knowledge gained from studying these asteroids could help us design spacecraft capable of withstanding extreme forces, construct artificial space habitats, or even develop new methods of asteroid mining. But beyond the scientific and practical implications, there's something deeply fascinating about these mysterious objects. They defy expectations, spin at impossible speeds, and challenge our understanding of the cosmos. They remind us that, no matter how much we think we know about space, there are still countless mysteries waiting to be uncovered. Perhaps, in the future, we'll finally unlock the secrets of ultra-rapidly spinning asteroids. Maybe we'll discover a new physical law that explains their existence. Or maybe we'll find that they're even stranger than we ever imagined. Until then, they remain as they always have, silent, spinning enigmas in the vastness of space, waiting for us to figure out what they truly are. The mystery deepens when we consider the incredible forces at play within these ultra-rapidly spinning asteroids. Based on our current understanding of physics, once an asteroid's rotation exceeds a certain limit, the outward forces should overcome its structural integrity, tearing it apart. And yet, these asteroids remain intact, defying the expectations of astronomers and challenging the very limits of what we know about celestial mechanics. One of the biggest questions is, what are these asteroids made of? The most common types of asteroids in our solar system are either rubble piles or solid monolithic bodies. Rubble pile asteroids are loosely held together by weak gravitational and cohesive forces, meaning they should break apart when spinning too fast. Monolithic asteroids, on the other hand, are thought to be single solid chunks of rock or metal, making them more resistant to rotational forces. But even the strongest materials we know of, such as iron-nickel alloys, should still have a breaking point. So how do these asteroids resist being torn apart? One possibility is that they contain materials with properties unlike anything we've seen before. There could be unknown chemical compositions or structural formations that allow them to maintain their integrity under extreme rotational stress. If these asteroids contain ultra-dense metals or exotic mineral structures, their internal cohesion could be far stronger than we previously believed possible. Another possibility is that some of these asteroids have an internal mechanism that actively redistributes their mass. If there are pockets of loose material inside, centrifugal forces could move these particles in a way that counteracts the stress of rapid spinning. This would be similar to how a figure skater pulls their arms in to spin faster, or extends them outward to slow down. If these asteroids contain shifting materials inside, they might be able to regulate their rotation dynamically. However, this raises an even bigger question: how do these asteroids start spinning so fast in the first place? The YORP effect, where sunlight heats up an asteroid's surface unevenly and causes it to spin, is a leading explanation. Over millions of years, this slow but constant force could gradually accelerate an asteroid to ultra-fast speeds. But there's a major problem with this idea. If the YORP effect were the only force at work, we would expect a smooth progression of spin rates among asteroids, some slow, some fast, and everything in between. Instead, we see an unusual pattern. Many asteroids spin at normal speeds, but a select few spin at extreme rates, with very few in between. This suggests that another force is at work, one that suddenly accelerates certain asteroids rather than gradually increasing their spin over time. Some researchers have suggested that violent cosmic collisions could be responsible. If an asteroid were struck by another object at just the right angle and speed, the impact could impart massive rotational energy, sending it into a rapid spin. However, this scenario has its own issues. If high-speed collisions were the primary cause, we should see many more fast-spinning asteroids than we currently do. Additionally, these impacts should leave visible scars or fractures on the asteroid's surface, but many of these rapidly spinning bodies appear relatively smooth and intact. Another theory is that these asteroids may have undergone close encounters with massive planets. If a small asteroid passed near Jupiter or Saturn, the immense gravitational forces could act like a slingshot, imparting extreme rotational energy. These gravitational interactions, known as tidal torques, could theoretically spin up an asteroid to incredibly high speeds. But again, this theory has gaps. If planetary flybys were the main cause, we should see more fast-spinning asteroids near the orbits of gas giants, yet these objects appear scattered throughout the solar system. There's also the tantalizing possibility that some of these asteroids didn't originate in our solar system at all. Interstellar objects, ejected from other star systems, could be traveling through our cosmic neighborhood, bringing with them extreme rotational properties that don't conform to what we expect from typical solar system asteroids. If some of these ultra-rapidly spinning asteroids are actually interstellar visitors, they could carry materials, structures, or even clues about the nature of other planetary systems. And then, there's the most controversial idea of all: could any of these objects be artificial? The thought may seem far-fetched, but scientists have already speculated about the possibility of alien probes drifting through space. If an ancient civilization sent out automated spacecraft, they might have become coated in dust and debris over time, making them appear like ordinary asteroids. If such a probe still contained a functioning internal mechanism, it could be spinning rapidly due to leftover propulsion systems, gyroscopic stabilization, or an unknown technology. While there is no direct evidence to support this idea, the unusual behavior of some ultra-fast spinning asteroids continues to raise eyebrows. Some of these objects exhibit near-perfect symmetry, an unusual feature for naturally formed asteroids. Others have strangely reflective surfaces, hinting at the possibility of unusual compositions. Could it be that, hidden among the countless rocks drifting through space, there are relics of ancient technology waiting to be discovered? But even if these asteroids are entirely natural, studying them could lead to revolutionary discoveries. If we can understand how these objects withstand extreme rotational forces, we might learn new principles of material science that could help us build stronger spacecraft, develop better engineering techniques, or even unlock new ways of stabilizing space structures. If these asteroids contain rare materials, they could also become valuable targets for future asteroid mining missions. Yet, despite our growing curiosity, studying these objects remains a significant challenge. Observing them from Earth is difficult because their rapid motion makes them hard to track with telescopes. Sending probes to study them up close would be even harder. A spacecraft attempting to land on a rapidly spinning asteroid would face immense challenges. The extreme centrifugal forces would make it almost impossible to attach to the surface, and any attempt to drill or take samples could result in the probe being flung away before it could collect meaningful data. One possible solution would be to design a spacecraft that could hover near the asteroid rather than landing. By deploying high-speed cameras, laser mapping systems, and spectrometers, scientists could analyze the asteroid's composition, rotation, and structural integrity without direct contact. Another approach could be to develop robotic drones capable of making brief, controlled contact with the asteroid's surface before being ejected back into space with a sample. Whatever the approach, the study of ultra-rapidly spinning asteroids represents one of the most exciting frontiers in space exploration. These objects challenge our understanding of physics, raise profound questions about the forces shaping our solar system, and offer the possibility of discovering new materials, or even interstellar visitors. They remind us that, despite all we have learned about the cosmos, there are still mysteries lurking in the darkness, waiting to be solved. And perhaps, one day, we will uncover the true nature of these enigmatic objects. Whether they turn out to be natural wonders, interstellar travelers, or something even more extraordinary, one thing is certain: the universe still holds secrets that defy explanation. The biggest challenge in solving the mystery of ultra-rapidly spinning asteroids is that they are incredibly difficult to observe. Unlike larger celestial objects such as planets or even moons, these asteroids are often tiny, sometimes only a few meters across. Their rapid rotation makes it hard for telescopes to get a clear, detailed look at their surfaces. Instead of seeing a stable, well-defined shape, astronomers often detect only flickering reflections of light, making it challenging to determine their exact structure, composition, or even whether they are solid or rubble piles. To work around this problem, astronomers use a combination of techniques. One of the most important tools is light curve analysis. This method involves measuring how an asteroid's brightness changes over time as it rotates. If an asteroid is spinning rapidly, its brightness will fluctuate in a predictable pattern based on its shape and surface reflectivity. By carefully analyzing these light fluctuations, scientists can make educated guesses about the asteroid's dimensions, rotation speed, and whether it has an irregular shape. Another key method is radar imaging. By bouncing radio waves off an asteroid and analyzing the returning signals, scientists can build rough 3D models of these objects. This technique has been crucial in studying near-Earth asteroids, revealing details such as surface roughness, possible craters, and even signs of complex rotation patterns. Some ultra-fast spinning asteroids have shown signs of non-principal axis rotation, meaning they aren't just spinning in one simple direction but instead tumbling chaotically through space. This chaotic tumbling raises even more questions. If an asteroid were a simple solid body, we would expect it to eventually settle into a stable rotation over time due to internal friction and external forces like solar radiation. But some ultra-fast rotators appear to be tumbling unpredictably, suggesting that they may have undergone recent violent disruptions, possibly collisions with other space debris or sudden mass ejections due to internal stresses. Another approach to studying these asteroids involves analyzing their spectral signatures. By examining how they reflect different wavelengths of light, astronomers can estimate their composition. Some ultra-fast spinning asteroids appear to be made of common rocky materials, while others show hints of metallic content. One of the most puzzling aspects of ultra-fast rotators is their distribution. These objects don't appear to be randomly scattered throughout the solar system. Instead, they tend to cluster in certain regions, such as the near-Earth asteroid population and the inner main belt. This suggests that whatever process is accelerating these asteroids is more active in specific areas. If these high-speed rotations were purely the result of the YRP effect, we might expect them to be evenly distributed. But the fact that they appear in clusters hints at a more complex set of influences, possibly including gravitational interactions with larger planets, past collisions, or even unseen forces that we don't yet understand. Another intriguing mystery is the longevity of these asteroids. How long can an object spin at such extreme speeds before something dramatic happens? Simulations suggest that most rubble-pile asteroids should eventually shed mass or completely disintegrate once they exceed a critical spin rate. However, we still detect ultra-fast rotators that have seemingly persisted for long periods. Could there be self-regulating mechanisms at work? Perhaps as these asteroids reach extreme speeds, they eject just enough material to stabilize themselves without fully breaking apart. This possibility brings us to the idea of asteroid fragmentation. Some astronomers believe that ultra-fast spinning asteroids could be the source of many smaller asteroids and meteoroids. If a parent body spins too fast, it could start shedding material in a way similar to how a rapidly spinning water droplet might break apart. Over time, this process could produce families of smaller asteroids, some of which might eventually enter Earth's atmosphere as meteorites. Interestingly, some meteorites that have been recovered on Earth show signs that they were once part of a rapidly spinning body. Certain meteorites contain microscopic deformations and stress patterns that suggest they were ejected from their parent asteroid at high velocities. Could it be that some of the meteorites we find on Earth are fragments of former ultra-fast rotators that lost their battle against centrifugal forces? If this is true, then studying these asteroids isn't just about understanding space. It could also help us learn more about the history of meteor impacts on Earth. If we can determine which types of ultra-fast rotators are most likely to break apart and send fragments our way, we could improve our ability to predict potential future impacts. This also ties into another important question: could ultra-fast spinning asteroids pose a threat to Earth? Most large asteroids that could impact our planet are well tracked, and none of them currently pose an imminent danger. However, ultra-fast rotators present a different kind of risk. Because they are so small and rapidly spinning, they can be harder to detect and track accurately. Some scientists worry that these asteroids could undergo sudden changes, such as breaking apart or changing their trajectory due to spin-induced mass ejection, making them unpredictable compared to more stable asteroids. This is one reason why missions to study and even deflect asteroids are becoming more important. NASA's DART, Double Asteroid Redirection Test, mission demonstrated that it is possible to change an asteroid's trajectory by deliberately crashing a spacecraft into it. But what if an asteroid is spinning at extreme speeds? Would an impact have the intended effect, or would it create unpredictable secondary fragments? These are the kinds of questions that scientists are eager to answer. One of the best ways to get definitive answers would be to send a dedicated space mission to study an ultra-fast spinning asteroid up close. While many asteroid missions have focused on larger, slower rotating targets, a probe designed to study a high-speed rotator could provide groundbreaking insights. Such a mission could attempt to land instruments on the asteroid's surface, or even deploy a swarm of small drones to study the asteroid from multiple angles. If we could retrieve samples from one of these asteroids, we might finally solve some of the biggest mysteries surrounding their structure and composition. Are they truly monolithic, or do they contain hidden pockets of loose material? Do they hold exotic minerals or metal alloys that could explain their resilience? And most intriguingly, could any of them carry signs of interstellar origins? Even if we don't send a mission soon, advances in ground-based and space-based telescopes could still help us unravel these mysteries. The upcoming Vera C. Rubin Observatory, for example, will provide unprecedented data on small asteroids, potentially identifying more ultra-fast rotators and allowing us to track their long-term evolution. Meanwhile, telescopes like the James Webb Space Telescope could analyze their spectral properties with incredible precision, helping us understand their compositions in greater detail. Ultimately, the study of ultra-rapidly spinning asteroids is about more than just understanding a peculiar space phenomenon. These objects challenge our understanding of physics, raise questions about the nature of matter, and could even provide clues about the broader history of our solar system. As technology advances and our ability to explore deep space improves, these asteroids may reveal secrets that we can't even begin to imagine. And if there's one thing that history has taught us about space exploration, it's that the biggest discoveries often come from the most unexpected places. Perhaps the answer to some of the universe's most profound mysteries is hiding in the rapid spin of an unassuming asteroid, waiting for us to look a little closer. The more we learn about ultra-rapidly spinning asteroids, the more questions emerge. One of the biggest challenges in studying these objects is that they defy many of our expectations about how celestial bodies should behave. If an asteroid is spinning at thousands of revolutions per minute, what keeps it from flying apart? And if it does break apart, what happens to its fragments? Are they simply scattered into space, or do they follow predictable patterns? One possibility is that some of these asteroids exist in a delicate balance between destruction and stability. They might be shedding tiny amounts of material constantly, effectively slowing their own rotation over time. This would mean that some of these asteroids are not permanent features of the solar system, but rather temporary phenomena that eventually self-destruct. If that's the case, then we might be witnessing the final stages of some of these asteroids before they completely disintegrate. But that raises another mystery. Why do some ultra-fast rotators seem to last much longer than they should? If they are constantly losing material, why don't they spin themselves into oblivion? One hypothesis is that some of these asteroids might have internal structures that reinforce their stability. For example, some could be held together by electrostatic forces or weak chemical bonding between dust particles. Others might have a layered composition, with denser materials in the core preventing the asteroid from breaking apart. Another possibility is that some of these asteroids are not entirely natural. While the vast majority of asteroids are formed through natural processes, there is always the question of whether some objects in space could have been altered, or even created, by unknown forces. Could some ultra-fast rotators be remnants of ancient spacecraft, artificial probes, or other extraterrestrial constructs that have long since lost their original purpose? While this might sound like science fiction, the idea of non-natural objects existing in space is not entirely implausible. For example, some astronomers have suggested that certain unusual objects in the solar system, such as the interstellar visitor Oumuamua, could be artificial in origin. While no conclusive evidence has been found, the idea that some asteroids might have unexpected origins is worth considering. If an ultra-fast spinning asteroid turned out to have an unnatural composition, it would raise profound questions about the history of our solar system and whether intelligent civilizations have left traces in deep space. But even if all ultra-fast rotators are entirely natural, they still hold secrets that could change our understanding of planetary formation. Some of these asteroids might be remnants of ancient collisions between planets or large moons. If they contain material from the deep interiors of those bodies, they could provide direct evidence of what lies beneath the surfaces of planets like Mars, Venus, or even Earth itself. One way to investigate this would be to analyze the mineral composition of these asteroids. If some ultra-fast rotators contain minerals that can only form under extreme pressure, such as those found in planetary cores, then it would suggest that they are fragments of much larger, long-destroyed worlds. This could help us piece together the history of the solar system and understand how planets form, evolve, and sometimes even get obliterated. Another mystery is whether these asteroids play a role in the formation of new celestial bodies. If they are constantly shedding material, could their debris eventually coalesce into new asteroids or even small moons? Some models suggest that small, rapidly spinning asteroids could act as seeds for larger structures, accumulating dust and debris over millions of years until they form something more stable. If this is true, then ultra-fast rotators might be an important part of the ongoing cycle of planetary evolution. They might not just be objects on the verge of destruction, they could also be the building blocks of future worlds. This raises an even more fascinating question. Could some of the planets and moons in our solar system have started as ultra-fast spinning asteroids billions of years ago? If so, studying these objects could help us understand the very origins of planetary systems. Even beyond the solar system, ultra-fast spinning asteroids could have cosmic significance. If similar objects exist in other star systems, they could tell us about how planets and asteroids form elsewhere in the universe. Some exoplanet studies suggest that high-speed rotation might be common among small rocky bodies, meaning that ultra-fast rotators might not be rare at all. They might just be difficult to detect from Earth. Future space telescopes might be able to identify these objects in distant star systems, helping us compare them to the ones we see in our own solar system. If we find that ultra-fast spinning asteroids are common throughout the universe, it would suggest that they play a fundamental role in the development of planetary systems. This could even have implications for the search for extraterrestrial life, since the distribution and behavior of small celestial bodies can influence the formation of habitable planets. One of the most exciting possibilities for future research is the idea of sending a spacecraft to land on an ultra-fast spinning asteroid. While this would be incredibly challenging due to the asteroid's rapid rotation, advances in autonomous spacecraft technology might make it possible. If we could successfully land a probe on one of these asteroids, we could directly study its composition, internal structure, and even the forces that keep it together. Some space agencies have proposed missions that could use harpoons or tethers to anchor a spacecraft to a fast-rotating asteroid. Others have suggested using robotic arms or inflatable landing pads that could adapt to the asteroid's motion. If a mission like this were successful, it could provide some of the most detailed data ever collected about these enigmatic objects. But even if we don't land on one anytime soon, continued observations from ground-based telescopes and space observatories will keep revealing new insights. Every time we discover a new ultra-fast rotator, we add another piece to the puzzle. And with each new discovery, we get one step closer to understanding one of the strangest and most fascinating phenomena in our solar system. The universe is full of mysteries, but few are as perplexing as ultra-rapidly spinning asteroids. These objects challenge our understanding of physics, hint at unknown forces at work, and might even provide clues about the origins of planets. As we continue to explore space, these asteroids will remain one of the most intriguing puzzles waiting to be solved. Ultra-rapidly spinning asteroids are not just scientific curiosities, they are also potential threats. The more we learn about them, the more we realize that some of these objects might eventually cross paths with Earth. While most asteroids that pass near our planet rotate at moderate speeds, an ultra-fast rotator could behave unpredictably. Its high rotation rate could make it more difficult to track, especially if it undergoes sudden shifts in trajectory due to material shedding or internal structural changes. One major concern is how these asteroids interact with Earth's atmosphere if they ever enter it. Most asteroids that reach our planet burn up due to friction with the air, creating meteors. However, if an ultra-fast rotator enters the atmosphere, its high-speed rotation could create unique effects. Depending on its shape and structure, it might break apart in an unusual way, sending debris in unpredictable directions. Instead of a single impact point, it could result in multiple smaller fragments striking different areas. This raises an important question. Could an ultra-fast spinning asteroid be responsible for past impact events on Earth? Scientists have studied craters from ancient asteroid collisions, but in most cases, they assume the impacting body was relatively stable. If a past asteroid impact involved an ultra-fast rotator, the event might have left a different kind of signature, possibly explaining some of the more unusual impact sites found around the world. There's also the possibility that some of these asteroids could have played a role in delivering key ingredients for life. Some theories suggest that the building blocks of life, organic molecules, amino acids, and even water, could have arrived on Earth via asteroids. If ultra-fast rotators are particularly good at shedding material, they might have been even more effective at spreading these essential compounds across the early solar system. This leads to another mystery. Could ultra-fast spinning asteroids have helped spread life beyond Earth? If an asteroid containing organic molecules was ejected from our solar system due to its rapid rotation, it could have carried these ingredients into deep space, potentially seeding other planets. This idea, known as panspermia, suggests that life might not have started on Earth alone but could be a cosmic phenomenon, with planets exchanging biological material over vast distances. Even if ultra-fast rotators didn't directly seed life, they could still influence the habitability of planets. If one of these asteroids were to collide with an exoplanet in another star system, it could alter the planet's atmosphere, change its climate, or even create conditions that make life more likely to develop. One of the most puzzling aspects of these asteroids is their ability to resist breaking apart. According to classical physics, any object spinning too fast should be torn apart by centrifugal forces. Yet, some ultra-fast rotators remain intact for millions of years. This suggests that their internal structure might be very different from what we expect. One possibility is that some of these asteroids are made of a type of material we haven't encountered before. Perhaps they contain exotic minerals or unknown forms of bonding that allow them to withstand incredible rotational forces. If we were to analyze a sample from one of these asteroids, we might discover materials that challenge our understanding of chemistry and physics. Another possibility is that these asteroids are held together by forces we don't fully understand. Some researchers have proposed that electrostatic charges could play a role, especially for smaller asteroids with high surface area-to-mass ratios. If static electricity helps keep them together, then ultra-fast rotators might be revealing new physics that could one day be applied to space technology. Then there's the question of how these asteroids got their extreme spin rates in the first place. Some theories suggest that they could have been part of larger bodies that were torn apart in massive collisions. If a planetary collision occurred billions of years ago, it might have created fragments that started spinning at extreme speeds due to the sheer force of the impact. Another idea is that some ultra-fast rotators might have been influenced by gravitational interactions with larger planets. If an asteroid passed close to Jupiter, for example, the planet's immense gravity could have caused it to accelerate its rotation. Over time, repeated gravitational encounters could push some asteroids to the edge of their structural limits. Yet another possibility is that solar radiation plays a role. The YORP effect, a phenomenon where sunlight gradually alters an asteroid's rotation over time, could cause some objects to spin faster and faster. If this effect is more powerful than we currently estimate, then it might be responsible for creating ultra-fast rotators. If this is true, it means that new ultra-fast spinning asteroids are still being created today. As long as sunlight continues to interact with small asteroids, some of them might gradually increase their spin rates until they reach incredible speeds. This means that the population of ultrafast rotators is not static, it is constantly evolving, with some asteroids slowing down while others speed up. This also means that our ability to predict their behavior is limited. If an asteroid's rotation can change significantly over time, then an object that is relatively stable today might become an ultrafast rotator in the future. This makes tracking these asteroids even more important, as their properties could shift unexpectedly. Some ultrafast spinning asteroids might even be capable of ejecting material into interstellar space. If an asteroid sheds fragments at high enough speeds, some of those fragments could escape the gravitational pull of the solar system entirely. This means that ultrafast rotators might be contributing to the population of interstellar objects, just like Oumuamua, the mysterious visitor from outside our solar system. If we could analyze one of these ejected fragments, we might gain insight into how material travels between star systems. Could ultrafast spinning asteroids be sending tiny pieces of the solar system to distant worlds? If so, it might be possible that fragments from other star systems have already reached us, carrying clues about the environments of planets orbiting distant stars. There's also the possibility that ultrafast spinning asteroids exist in even greater numbers in other parts of the universe. If certain conditions make them more likely to form, then star systems with different compositions or histories might have even more of these high-speed objects. This could mean that ultrafast rotators are not just a local phenomenon but a common feature of the cosmos. With new telescopes coming online in the next few decades, we might soon get answers to some of these questions. The Vera C. Rubin Observatory, for example, will scan the sky in unprecedented detail, potentially discovering thousands of new asteroids, including more ultrafast rotators. Other upcoming missions, like the European Space Agency's Hera spacecraft, will study asteroid behavior in ways never done before. If we ever want to send humans beyond Earth, understanding ultrafast rotators will be crucial. Any future missions to asteroids for mining, research, or potential colonization will need to account for these rapidly spinning objects. If an asteroid is moving unpredictably, it could pose a major challenge for space travel, requiring new technologies to safely navigate around or land on these bodies. One day, we might even find a way to harness the energy of these spinning asteroids. If we could attach devices to them that convert rotational energy into usable power, we could create a new source of energy for future space missions. This would turn ultra-fast rotators from a mystery into a valuable resource for deep space exploration. Ultimately, ultra-rapidly spinning asteroids represent one of the most fascinating frontiers in space science. They challenge our understanding of physics, raise new questions about the evolution of celestial bodies, and might even hold secrets about the origins of life. As we continue to study them, we can only expect more surprises, because if there's one thing the universe has taught us, it's that the more we discover, the more mysteries we uncover. Ultra-rapidly spinning asteroids challenge many of our assumptions about how celestial bodies behave in space. The more we study them, the more we realize they don't fit neatly into our existing models. They defy expectations by spinning at speeds that should, in theory, cause them to disintegrate. They shed material in unpredictable ways. They might even transport organic compounds across the cosmos. But perhaps the biggest mystery of all is what they could tell us about the fundamental forces that govern the universe. One of the most intriguing possibilities is that these asteroids could be linked to dark matter or dark energy. Scientists still don't fully understand what makes up the majority of the universe. While we can observe ordinary matter, the kind that forms planets, stars, and galaxies, most of the universe appears to be composed of something else entirely. Dark matter doesn't emit or reflect light, yet its gravitational effects can be detected on a cosmic scale. Dark energy, on the other hand, seems to be responsible for the accelerating expansion of the universe. Could ultra-fast rotators provide clues about these invisible forces? Some researchers have speculated that if dark matter interacts with ordinary matter in unexpected ways, it might help certain asteroids maintain their extreme spin rates. If a high-speed asteroid were somehow absorbing or interacting with dark matter, it might explain why some of these objects don't break apart as expected. This is purely speculative, but it's an idea worth exploring as we continue to study the nature of both dark matter and fast-spinning asteroids. There's also the question of whether ultra-fast rotators could help us refine our understanding of gravity itself. Newtonian physics tells us that any object spinning too fast will eventually be torn apart by centrifugal force. But what if there are subtle gravitational effects that we haven't accounted for? What if the behavior of these asteroids hints at new aspects of physics that we haven't yet discovered? One possibility is that they are affected by gravitational anomalies. Some scientists believe that certain regions of space might have slightly different gravitational properties due to variations in the distribution of mass. If ultra-fast rotators tend to cluster in certain parts of the solar system, it could suggest that localized gravitational effects are influencing their behavior. This could mean that space itself is not as uniform as we once believed, opening the door to entirely new theories about how the universe works. Another intriguing idea is that some of these asteroids could be remnants of ancient cosmic events that we have yet to fully understand. Could ultra-fast rotators be evidence of past interstellar collisions? If a high-speed object from another star system collided with a local asteroid billions of years ago, the resulting debris might include fragments that inherited extreme spin rates. This could mean that at least some of the ultra-fast rotators we see today are actually pieces of interstellar objects that wandered into our solar system long ago. If this is true, then studying these asteroids might give us a glimpse into the conditions of other star systems. By analyzing their composition, we could determine whether they contain elements or isotopes that are rare in our solar system but common elsewhere in the galaxy. This could help us understand the diversity of planetary systems beyond our own, shedding light on how planets and moons form in different environments. Of course, if ultra-fast rotators are capable of shedding material at high speeds, then it's also possible that they could be spreading pieces of themselves across the solar system. Some of these fragments might have ended up on Earth, buried within ancient meteorites. Scientists have long studied meteorite samples to learn about the history of the solar system. But what if some of these rocks originated from ultra-fast spinning asteroids? If we could identify a meteorite that came from one of these objects, it might provide direct evidence of their unique properties. There's even a possibility that ultra-fast rotators could influence the asteroid belt in ways we don't fully understand. The asteroid belt between Mars and Jupiter is home to millions of rocky bodies, but it's not a static environment. Collisions and gravitational interactions constantly change the distribution of material. If some ultra-fast rotators are located within the asteroid belt, they might be acting as natural disruptors, sending smaller asteroids on unpredictable trajectories. This could have major implications for planetary defense. If an ultra-fast spinning asteroid were to send debris hurtling toward Earth, we might have less time to react than we think. Unlike more predictable asteroid paths, which can be calculated years in advance, debris from a rapidly rotating object could be harder to track. This means that understanding the behavior of these asteroids isn't just an academic exercise. It could one day be essential for protecting our planet. NASA and other space agencies are already working on ways to deflect hazardous asteroids, but ultra-fast rotators could pose unique challenges. If one of these objects were headed for Earth, standard deflection methods might not work as expected. A kinetic impactor, for example, might not be effective if the asteroid is shedding material unpredictably. In the future, we might need entirely new strategies to deal with threats from high-speed rotating objects. One idea is to use robotic spacecraft to study ultra-fast rotators up close. If we could send a probe to one of these asteroids, we could learn more about their structure, composition, and behavior. This would help us determine how best to mitigate any potential threats. It could also reveal new insights into their origins, answering some of the biggest questions about how they formed and why they behave the way they do. In the long run, understanding ultra-fast rotators could also have practical applications for space travel. If we ever establish mining operations on asteroids, we'll need to account for objects that spin at extreme speeds. Traditional mining techniques might not work on these asteroids, meaning we'd have to develop specialized equipment. If we can learn how to stabilize or manipulate their spin, we might be able to extract valuable resources more efficiently. There's also the potential for harnessing their energy. If an asteroid is already spinning at an extremely high speed, could we use that motion to generate power? Spacecraft that land on these objects might be able to tap into their rotational energy, using it as a source of electricity. This could be a game-changer for long-duration space missions, providing a renewable energy source in deep space. As our technology advances, we might even find ways to alter the rotation of these asteroids. If we can control their spin, we could potentially steer them to safer locations or even use them as mobile resource hubs. Imagine a future where we can redirect ultra-fast rotators to positions where they can be more easily studied or mined. This would turn them from unpredictable hazards into valuable assets. Ultimately, ultra-rapidly spinning asteroids represent one of the greatest unsolved mysteries in space science. They challenge our understanding of physics, force us to rethink how asteroids evolve, and could even hold clues to the origins of life. As we continue to explore the solar system, we're bound to discover even more surprises about these high-speed wanderers. With each new observation, we peel back another layer of the mystery, but for every question we answer, new ones emerge. Why do some asteroids spin so fast while others remain stable? What role do they play in the larger cosmic picture? Could they be linked to unknown forces shaping the universe? The answers to these questions could change the way we see not just our solar system, but the entire cosmos. And as we develop better telescopes, send more missions into deep space, and refine our understanding of asteroid physics, we may finally unlock the secrets of these enigmatic objects. Until then, ultra-fast spinning asteroids will remain one of the most fascinating and perplexing wonders of the universe. Ultra-rapidly spinning asteroids force us to reconsider the very nature of matter and space. At their extreme speeds, the forces acting on them seem to defy our expectations, raising deeper questions about the strength of materials in the vacuum of space. If an asteroid can spin beyond what we believe to be its structural limit, then either our models of cohesion and microgravity are incomplete, or there are unknown reinforcing factors at play. One possibility is that these asteroids are held together by forces beyond just gravity and friction. Some scientists suggest that van der Waals forces, weak intermolecular attractions, may play a role in stabilizing small asteroids, preventing them from disintegrating despite their rapid rotation. These are the same forces that allow geckos to stick to walls or find dust particles to cling together. In the microgravity environment of space, where weight is negligible, these subtle forces might be stronger than we previously thought, acting as a kind of molecular glue. If this theory is correct, then ultra-fast rotators might be providing us with a natural laboratory to study how materials behave in low-gravity environments. This has significant implications for future space exploration and colonization. Understanding these forces could help engineers design better structures for space stations, lunar bases, or even asteroid mining operations. If van der Waals forces can keep an asteroid intact at extreme speeds, they might also help us develop materials that can withstand the harsh conditions of space without requiring traditional fasteners or adhesives. But what if some ultra-fast rotators are held together by something else entirely? Could magnetic fields be playing a role? Some asteroids contain significant amounts of metal, including iron and nickel. If an asteroid were highly magnetized, it might resist breaking apart through electromagnetic attraction. While no strong evidence has been found for this yet, it's a hypothesis worth investigating. If true, it could help explain why some ultra-fast spinning asteroids maintain their shape against all odds. Beyond their physical composition, there's also the question of how these asteroids attain such extreme rotation speeds in the first place. The YORP effect is one explanation, but are there other mechanisms at play? Some astronomers speculate that certain ultra-fast rotators may have been involved in violent past collisions that imparted a high angular momentum. If a larger asteroid broke apart due to an impact, smaller fragments might have inherited rapid spin rates. Over time, if these fragments remained relatively intact, they could have preserved their high-speed rotation for millions or even billions of years. This idea leads to another intriguing possibility. Could some ultra-fast rotators actually be remnants of a much larger body? If so, then studying them might allow us to reconstruct ancient celestial events, much like archaeologists piecing together history from scattered ruins. If we could trace back their origins, we might uncover evidence of massive asteroid collisions that shaped the early solar system. Even more exciting is the potential link between ultra-fast rotators and planetary formation. Some models suggest that before planets fully formed, the solar system was filled with rapidly spinning debris. If these objects are leftover relics from that chaotic era, they could provide insight into the conditions that led to the formation of Earth and other planets. There's also the question of whether these asteroids might have transported organic molecules across space. Some meteorites found on Earth contain amino acids, the building blocks of life. If ultra-fast rotators are shedding material at high speeds, then it's possible that some of this material could have made its way to Earth in the distant past. Could these asteroids have played a role in seeding life on our planet? This brings us to the possibility of ultra-fast rotators acting as natural delivery systems for complex molecules. If they can eject material into space, then some of that debris could end up on other planets or moons. In theory, if a fast-spinning asteroid were to pass through a region of space containing organic compounds, it might capture and later release those molecules elsewhere. This could be a mechanism for spreading the ingredients of life throughout the solar system, or even the galaxy. Could this be part of a broader cosmic pattern? If ultra-fast rotators exist around other stars, then they might play a role in spreading material across interstellar distances. If we ever detect a rapidly spinning asteroid in another solar system, it might provide clues about whether the same processes that shaped our solar system are happening elsewhere. All of this leads to a fascinating idea. Could ultra-fast spinning asteroids be key players in the grand cycle of planetary evolution? If they contribute to both destruction, through collisions, and creation, by delivering material, then they might be more than just anomalies. They could be essential components of the universe's natural recycling system, constantly reshaping celestial bodies across billions of years. Another mystery surrounding ultra-fast rotators is their unusual surface features. Observations suggest that some of them have elongated shapes, or even appear to be spinning so fast that they stretch apart into multiple connected segments. This raises the question, could some of these asteroids actually be binary objects? A binary asteroid system consists of two bodies orbiting each other, often held together by weak gravitational forces. If a high-speed asteroid were once part of a binary system, then its rotation could have been influenced by interactions with its companion. In some cases, if one object spun up too quickly, it might have flung off material that later recoalesced into a secondary body. If we can find evidence that ultra-fast rotators frequently have companions, it would reshape how we think about their evolution. It might mean that instead of being lone wanderers, many of them are actually part of dynamic, ever-changing systems where material is constantly exchanged between bodies. There's even the possibility that some ultra-fast rotators are temporary objects, asteroids that are in the process of breaking apart before our eyes. If an asteroid were to reach an extreme spin rate, it might begin shedding material at an increasing pace until it disintegrates entirely. This could mean that some of the fastest spinning asteroids we see today might not exist in their current form for much longer. If we can observe one of these asteroids undergoing such a transformation, it would provide a rare opportunity to witness planetary physics in action. It could give us a real-time look at how space debris evolves, breaks apart, and potentially reforms into new objects. But the ultimate question remains, are ultra-fast rotators unique to our solar system, or are they common throughout the universe? If we discover similar objects orbiting other stars, it would suggest that extreme asteroid rotation is a fundamental feature of planetary systems everywhere. It might mean that wherever planets form, ultra-fast rotators emerge as a natural consequence of that process. And if that's the case, then these objects could be far more significant than we ever imagined. They might be key players in shaping the structure of solar systems, influencing everything from asteroid belts to planetary collisions. They might even play a role in determining which planets are habitable by distributing water-rich material across space. The more we study ultra-fast rotators, the more questions emerge. They challenge our understanding of material strength, cosmic collisions, planetary formation, and even the spread of life. They exist at the edge of what we think is possible, defying our models and forcing us to rethink the laws of physics. One day, we might send a mission to study an ultra-fast spinning asteroid up close. We might land a probe on its surface, drill into its core, and analyze its composition in detail. We might finally unlock the secrets of how these extreme objects form, how they survive, and what role they play in the grand cosmic picture. Until then, ultra-fast rotators remain one of the most baffling mysteries of space, enigmatic, unpredictable, and full of surprises. Every time we look deeper, we uncover more layers of complexity, more unknowns, and more possibilities. And perhaps, somewhere out there, one of these spinning wanderers holds the key to understanding something far bigger than we ever imagined. Ultra-fast rotators may also be connected to one of the biggest questions in planetary science. How do asteroid families form and evolve over time? When a large asteroid is struck by another object, it often breaks apart into smaller fragments, creating a family of related asteroids. These fragments can inherit rotation from the impact, and some of them may end up spinning at extreme speeds. But what if certain ultra-fast rotators didn't originate from collisions at all? There's a theory that some of them could have formed from the gradual buildup of angular momentum over time, rather than from a sudden impact. If this is true, it means that the processes shaping our solar system might be more gradual and complex than we ever thought. Instead of being formed in a violent event, some of these asteroids may have slowly evolved into their current state, their rotation speeds increasing over millions or even billions of years. This leads to another question: what happens if an ultra-fast rotator reaches its absolute spin limit? We know that if a rubble pile asteroid spins too fast, it will break apart. But for monolithic asteroids, solid rock bodies, the answer is less clear. Could there be a limit beyond which even solid asteroids disintegrate? And if so, could we ever witness such an event? If an asteroid were to spin so fast that it crossed a critical threshold, it might begin ejecting material in a steady stream. This could eventually lead to the formation of a ring system, similar to the rings of Saturn. While we typically associate rings with planets, some asteroids are known to have faint ring systems. Could these rings be the result of extreme spin rates? Could ultra-fast rotators be the missing link in understanding how asteroid rings form? Some scientists even speculate that a rapidly spinning asteroid might eventually flatten out into a disc-like shape due to centrifugal forces. If this were to happen, it would challenge our traditional understanding of what an asteroid can be. Instead of being a lumpy rock, an ultra-fast rotator at its extreme limit might start resembling something more akin to a flying saucer. While this might sound like science fiction, physics suggests that extreme spin could cause an asteroid's shape to become highly distorted. Another possibility is that some of these asteroids might be hollow. If an ultra-fast rotator had large internal voids, it could theoretically spin faster without breaking apart because there would be less mass pushing against its structural limits. This raises a fascinating question: could there be naturally occurring hollow asteroids in space? If so, how did they form? Were they once solid but gradually eroded from the inside out? Or were they always hollow, created by unknown processes in the early solar system? Some have even speculated that if a hollow asteroid were spinning fast enough, it might produce detectable signals similar to those of artificial objects. This has led to wild theories about whether certain ultra-fast rotators could be mistaken for something other than natural objects. While there's no solid evidence to support this idea, it highlights just how strange and unpredictable these asteroids are. Even without venturing into speculative territory, ultra-fast rotators are already rewriting what we know about asteroid physics. Their existence suggests that our understanding of how solid bodies behave in space is incomplete. They challenge our models of material strength, friction, and cohesion. They force us to reconsider the role of small-scale forces, such as electrostatic attraction and molecular bonding, in keeping asteroids intact. This has practical implications as well. If we ever attempt asteroid mining, understanding the structural limits of these objects will be crucial. If an asteroid can suddenly break apart due to rapid rotation, it could pose a serious risk to any mining operation. Future space missions might need to account for the possibility that an asteroid's rotation could change unexpectedly, either due to the YORP effect or external influences like spacecraft landings. Ultra-fast rotators might also influence planetary defense strategies. If we ever need to deflect an asteroid on a collision course with Earth, knowing its spin rate will be vital. A slow-rotating asteroid might be easier to push off course, while an ultra-fast rotator could behave unpredictably under external forces. If we tried to nudge it with an impactor or a gravitational tractor, its spin could cause it to react in unexpected ways, making deflection more complicated. This raises an intriguing idea. Could some asteroids naturally spin so fast that they become self-deflecting? If an asteroid's spin rate increased over time, could it eventually reach a point where it sheds enough mass to change its trajectory? Could ultra-fast rotators be a natural mechanism for preventing collisions with planets by gradually altering their own paths? These questions take us deeper into the mysteries of how asteroids interact with their surroundings. Some researchers believe that ultra-fast rotators could play a role in the long-term evolution of the asteroid belt. If certain asteroids reach extreme spin rates and then break apart, they might be responsible for creating much of the dust and debris that fills interplanetary space. If this is true, then ultra-fast rotators aren't just rare curiosities. They're fundamental players in shaping the solar system. They might be responsible for seeding space with tiny fragments that eventually become meteoroids. They might be the origin of some of the shooting stars we see in Earth's night sky. They might even be responsible for delivering water and organic compounds to planets and moons, influencing their potential for habitability. All of this makes ultra-fast rotators one of the most fascinating and underappreciated objects in space. They defy our expectations, challenge our understanding of physics, and raise profound questions about how the solar system operates. They exist on the edge of stability, constantly pushing the limits of what's possible for an asteroid. And yet, we still have so much to learn. Every new observation brings new surprises. Every new discovery forces us to rethink our assumptions. Ultra-fast rotators remind us that space is full of unknowns, and that sometimes, the strangest objects can teach us the most about the universe. If ultra-fast rotators are responsible for breaking apart and creating new debris in space, then they might also be a missing link in understanding how asteroid families evolve. When an asteroid breaks apart due to excessive spin, the fragments it sheds could go on to form new asteroids. Some of these fragments might themselves become ultra-fast rotators, continuing the cycle. Others might slow down over time, eventually becoming stable asteroids that contribute to the ever-changing population of the solar system. This cycle of fragmentation and reformation might even play a role in the formation of certain types of meteorites. If ultra-fast rotators are responsible for shedding small particles, then some of these particles might eventually enter Earth's atmosphere. This could explain why certain types of meteoroids seem to have unusual compositions or structures. They could be the remnants of asteroids that once spun at extreme speeds. But what if this process doesn't just affect small asteroids? Could ultra-fast rotation also influence the fate of much larger objects? If a large asteroid were to reach a critical spin rate, could it break apart into multiple smaller bodies, reshaping entire regions of the asteroid belt? Could this be a mechanism for creating asteroid clusters, where multiple asteroids share similar orbits because they originated from the same spinning parent body? This idea has led scientists to revisit certain asteroid families to see if they show signs of being influenced by rapid rotation. Some asteroid families appear to have members that share remarkably similar compositions, suggesting they came from the same source. But if that source was an ultra-fast rotator that broke apart, it would mean that spin isn't just a side effect of asteroid evolution, it's a key driver of how asteroids change over time. There's also the question of whether ultra-fast rotators could play a role in planetary formation. Some planetary scientists believe that before planets formed, the early solar system was filled with rapidly spinning debris. If certain objects reached ultra-fast rotation speeds and then broke apart, they might have contributed to the cloud of material that eventually coalesced into planets. If this theory is correct, then ultra-fast rotators aren't just a modern phenomenon. They've been around since the birth of the solar system. They may have influenced how planets formed, how moons were created, and even how the asteroid belt itself came to be. Some researchers have even suggested that rapidly spinning planetesimals in the early solar system could have affected how planetary rings formed, providing a link between asteroids and the vast ring systems we see around planets like Saturn and Uranus. This brings us to one of the biggest unknowns: how many ultra-fast rotators are out there? We know of only a small number, but that could be because they're difficult to detect. Since they spin so quickly, they don't reflect light in the same way as slower rotating asteroids, which means they could be hiding in plain sight. Some astronomers think that if we had better observation techniques, we might discover that ultra-fast rotators are far more common than we currently believe. If they are common, then they could be a major factor in shaping the evolution of the solar system. They might be responsible for more asteroid breakups than we realize. They might be influencing planetary surfaces by sending high-speed debris their way. They might even be a key piece of the puzzle in understanding how asteroids transition from solid bodies into loose rubble piles. And if ultra-fast rotators are affecting the evolution of the asteroid belt, then they might also be influencing planetary orbits. If certain asteroids shed material at high speeds, then the resulting debris could create subtle gravitational effects that alter the paths of nearby objects. Over millions of years, these tiny changes could add up, potentially playing a role in the long-term stability of the solar system. This leads to another wild but intriguing idea: could ultra-fast rotators ever act as natural propulsion systems? If an asteroid were to shed material in a consistent direction, then it might gradually change its own orbit, similar to how a spacecraft adjusts its trajectory by firing thrusters. While this effect would be extremely weak, over long periods, it could lead to noticeable shifts in an asteroid's path. Some researchers have even speculated that ultra-fast rotators could help explain why certain asteroids have unusual orbits. If a rapidly spinning asteroid slowly loses mass, then it might end up on a trajectory that doesn't match what we'd expect based on standard gravitational models. This could be why some near-Earth asteroids have orbits that seem difficult to explain. Perhaps they've been subtly altered by the effects of extreme spin. This raises a major question about asteroid deflection strategies. If we ever need to move an asteroid away from Earth, could we use spin to our advantage? Instead of trying to push an asteroid with a spacecraft, could we alter its spin rate in a way that causes it to naturally shift its orbit? Could ultra-fast rotation be harnessed as a tool for planetary defense? There's still a lot we don't know, but what's clear is that ultra-fast rotators are more than just oddities. They could be fundamental players in shaping the past, present, and future of the solar system. They challenge our understanding of physics, force us to rethink how asteroids evolve, and open up new possibilities for how we might one day interact with space. And yet, despite all this, we've only scratched the surface. There's still so much to learn, and every new discovery adds another layer of complexity to the mystery. Ultra-fast rotators remind us that even in a universe we've studied for centuries, there are still surprises waiting to be uncovered. If ultra-fast rotators are more common than we realize, then the implications stretch far beyond our current understanding. Imagine a scenario where a large portion of the asteroid belt consists of objects that are spinning at extreme speeds. This would mean that asteroid collisions, fragmentations, and even material exchanges between asteroids might be happening at rates much higher than we expected. It would also mean that the structure of many asteroids is far more fragile than we assume, which could have major consequences for future space missions. For example, if we were to send a probe to land on an asteroid without first understanding its spin rate, we could be in for a disaster. A spacecraft landing on an ultra-fast rotator might trigger an unexpected reaction. The sudden addition of weight, even if minimal, could destabilize the asteroid's delicate balance and cause it to shed material or even break apart. This would make asteroid landings much riskier than anticipated, and it would mean that any future asteroid mining operations would need to be extremely careful when selecting their targets. But what if we could harness the energy of these ultra-fast rotators instead of fearing them? If an asteroid is spinning at thousands of times per hour, then it already possesses an incredible amount of kinetic energy. Could there be a way to extract that energy for use in space missions? Some scientists have proposed using spinning asteroids as a form of natural energy storage, where spacecraft could dock with them and use their rotational energy to assist in maneuvering. While this idea is still in its early stages, it raises an interesting question. Could ultra-fast rotators be more than just space debris? Could they be resources waiting to be tapped? This brings up another question. Could ultra-fast rotators be influencing how material spreads throughout the solar system? If these asteroids are regularly shedding dust and small particles, then their influence might extend far beyond their immediate surroundings. Some of this material might drift into interplanetary space, potentially reaching other planets. If these particles contain water or organic molecules, then ultra-fast rotators might have played a role in delivering essential ingredients for life to Earth. This theory is especially intriguing when we consider that some of the fastest spinning asteroids are made of carbonaceous material, the same type of material that is rich in organic compounds. If ultra-fast rotators are constantly shedding pieces of themselves, then they might be one of the mechanisms by which life's building blocks are distributed throughout the cosmos. This could provide new insights into how planets like Earth ended up with the necessary materials for life to emerge. And if these asteroids are spreading organic material, could they also be responsible for seeding life elsewhere? Some researchers believe that if microbes can survive in space for long periods, then it's possible they could hitch a ride on asteroid fragments and travel between planets. This idea, known as panspermia, suggests that life on Earth might not have originated here at all. It could have been delivered by space debris, possibly from ultra-fast rotators ejecting material at high speeds. If this is true, then ultra-fast rotators might not just be remnants of the past. They could be active participants in spreading life throughout the universe. This leads to a much bigger question. If we find a rapidly spinning asteroid in another star system, could it be a sign that life has traveled there from another world? Could ultra-fast rotators be natural messengers, carrying the building blocks of life across the cosmos? The more we study these objects, the more we realize how much they challenge our understanding of physics. For example, some ultra-fast rotators appear to be defying what we know about material strength. Based on our models, a rock should only be able to spin so fast before it flies apart. Yet, some of these asteroids seem to be holding together at speeds that shouldn't be possible. This suggests that there might be unknown forces at play, perhaps electrostatic interactions, molecular bonding, or even some form of self-reinforcing structure that prevents them from breaking apart. If this is true, then our models of how asteroids behave need to be completely rethought. It could mean that there are entire categories of celestial objects that we don't yet understand. Objects that are held together by forces we have yet to fully explore. One of the biggest mysteries is whether ultra-fast rotators are a temporary phenomenon or a long-term state. Are these asteroids destined to eventually slow down, or will they maintain their extreme spin rates indefinitely? If they do slow down, what causes it? Do they eventually lose enough material that their spin stabilizes? Or do they interact with other celestial bodies in ways that gradually decrease their rotation speed? One possibility is that ultra-fast rotators might occasionally collide with other objects, which could either slow them down or, in some cases, increase their spin even more. If a small impact strikes an already fast-rotating asteroid at just the right angle, it could add even more angular momentum, pushing the asteroid closer to its ultimate speed limit. If this happens often enough, it could explain why some asteroids seem to be spinning near the theoretical breaking point. They might have been gradually accelerated by multiple impacts over time. But what happens if an ultra-fast rotator reaches a point where it can no longer hold itself together? Could there be a dramatic moment when it suddenly disintegrates, sending fragments flying in all directions? If so, could we ever witness such an event from Earth? Some astronomers believe that we might be able to detect the aftermath of an ultra-fast rotator breaking apart by looking for sudden increases in the amount of dust and debris in certain regions of the asteroid belt. If we ever spot a sudden burst of new material, it could be evidence that an ultra-fast rotator has finally reached its limit and disintegrated. If we could catch such an event in real time, it would give us an unprecedented look at how asteroids evolve and how material is redistributed in space. It might even help us answer some of the biggest questions about the origins of planets, moons, and other celestial bodies. Ultra-fast rotators are a reminder that space is far more dynamic than we often assume. Instead of being static, unchanging objects, asteroids are constantly evolving, shifting, and sometimes even destroying themselves in ways we're only beginning to understand. And as we continue to explore these mysteries, one thing is clear: there's still so much we don't know. Every time we look deeper, we uncover new surprises. Ultra-fast rotators might hold answers to some of the biggest questions about the solar system's history, the mechanics of celestial bodies, and even the spread of life itself. But to unlock those answers, we need more observations, more research, and more missions dedicated to studying these incredible objects. The more we learn, the closer we come to solving the puzzle of how ultra-fast rotators fit into the grand story of the universe. If we were to fully understand the role of ultra-fast rotators, we would need to rethink how we study asteroids altogether. Most of our current asteroid surveys focus on tracking their orbits, sizes, and general compositions. But when it comes to ultra-fast rotators, we need a much more detailed approach. We would need to map their exact spin rates, determine how their surfaces respond to different forces, and track any material they shed over time. One of the most promising ways to study these objects is through high-resolution radar imaging. By bouncing radio waves off an asteroid and analyzing the reflected signals, we can get an incredibly detailed picture of its shape and rotation. This technique has already revealed that some asteroids have bizarre, elongated shapes, possibly due to their rapid spin pulling them into distorted forms. But even radar has its limits. Some ultra-fast rotators are simply too small or too far away to be imaged with current technology. This means that, for now, a large portion of these asteroids remains invisible to us. It's likely that many more ultra-fast rotators are out there, waiting to be discovered. One way to find them would be to look for their unique light signatures. Since these asteroids spin so rapidly, they reflect sunlight in a highly irregular pattern. If we monitored their brightness over time, we might be able to detect fluctuations that reveal their extreme rotation. Some astronomers have already begun using this method, and the results suggest that ultra-fast rotators might be far more common than we once thought. But there's an even bigger challenge. How do we study an ultra-fast rotator up close? Unlike slower asteroids, which can be safely approached by spacecraft, an ultra-fast rotator poses a unique danger. Any probe attempting to land on its surface would have to deal with intense centrifugal forces that could make landing nearly impossible. If the asteroid is shedding material, that debris could also pose a serious threat to any approaching spacecraft. To solve this problem, scientists are exploring new mission concepts that could allow us to study these objects without needing to land on them. One idea involves using small, autonomous probes that could hover near an asteroid and take high-resolution images. These probes could also deploy tiny sensors onto the asteroid's surface, allowing us to measure its composition and internal structure without directly interfering with its spin. Another approach involves using spacecraft equipped with harpoons or anchors that could latch onto the asteroid without requiring a traditional landing. This would allow us to collect samples without disrupting the asteroid's delicate balance. Some mission proposals have even suggested using robotic arms to catch small pieces of debris as they're ejected from the asteroid's surface, providing valuable insights into the materials that make up these rapidly spinning bodies. If we could retrieve samples from an ultra-fast rotator, it would be a major breakthrough in planetary science. We could analyze the material in laboratories on Earth, looking for clues about how these asteroids formed and whether they contain any organic compounds. This could help us answer some of the biggest questions about the role asteroids have played in shaping the solar system. But beyond scientific curiosity, there's also a more practical reason to study ultra-fast rotators. Understanding these objects could be crucial for planetary defense. If one of these asteroids were ever to be on a collision course with Earth, its extreme spin would make it far more difficult to deflect than a regular asteroid. Traditional methods, like using a spacecraft to push an asteroid off course, might not work if the asteroid is already spinning wildly. Instead, we might need to develop entirely new deflection strategies that take an asteroid's spin into account. One possibility is using a gravitational tractor, a spacecraft that slowly pulls the asteroid off course using its own gravitational influence. Another idea is to use laser beams or solar sails to gently alter the asteroid's spin over time, gradually shifting its trajectory in a way that prevents an impact. Whatever the solution, one thing is clear: we need to learn as much as we can about ultra-fast rotators before we ever face a real threat from one. The more we understand their physics, the better prepared we'll be if we ever need to deal with one heading toward Earth. And there's still one more mystery that remains unsolved. Could ultra-fast rotators exist beyond our solar system? We already know that asteroids exist around other stars. These are known as exoasteroids. But could some of them be spinning at extreme speeds, just like the ones we see in our own solar system? If so, then ultra-fast rotators might not just be a local phenomenon. They could be a fundamental feature of asteroid evolution throughout the universe. If we ever detect one around another star, it would suggest that these objects form naturally under a wide range of conditions. It could mean that ultra-fast rotation is a key part of how small bodies evolve, no matter where they are in the cosmos. This could have major implications for our search for extraterrestrial life. If ultra-fast rotators are common in other planetary systems, then they might be spreading organic material in the same way they do in our solar system. This could mean that the ingredients for life are being transported across the universe more efficiently than we ever imagined. It's possible that ultra-fast rotators are one of the universe's many mechanisms for shaping planetary systems, redistributing material, and even influencing the emergence of life. They might not be mere space debris, they could be cosmic architects, playing a role in the grand structure of the cosmos. And yet, despite everything we've learned, we're still only at the beginning. The study of ultra-fast rotators is a relatively new field, and there are still so many unanswered questions. How many of them exist? What forces determine their maximum spin rate? Do they play a role in planet formation? Could they be linked to the origins of life itself? The only way to find out is to keep searching, keep exploring, and keep pushing the boundaries of what we know. Because every time we look deeper into the mysteries of space, we find that the universe is even stranger, more dynamic, and more fascinating than we ever imagined. Ultra-fast rotators challenge our very understanding of asteroid stability. In classical physics, there is a theoretical limit to how fast an asteroid can spin before it disintegrates due to centrifugal forces. This is known as the spin barrier, typically set around 2.2 hours for asteroids larger than 200 meters. But ultra-fast rotators defy this rule. Some spin in mere minutes, raising the question, how are they still intact? One possibility is that these asteroids are composed of a single, solid piece of rock, rather than being rubble piles held together by gravity. A monolithic asteroid could, in theory, withstand much higher spin rates than a loosely bound one. But this raises another issue: how did they form? Most asteroids are believed to be fragments of larger bodies that broke apart in collisions, and these fragments are usually piles of debris rather than single solid pieces. If ultra-fast rotators are monolithic, it suggests that some asteroids either never experienced such collisions or formed through a completely different process. Another hypothesis is that these asteroids might have internal forces holding them together. For example, they could have a high level of cohesion due to electrostatic forces or even molecular bonding at a microscopic level. If this is the case, then ultra-fast rotators might provide an entirely new perspective on how small bodies behave in space. But what if some of these asteroids are breaking apart, just very slowly? If an ultra-fast rotator is shedding material at a gradual pace, it might take centuries or even millennia before it fully disintegrates. Some astronomers believe that these asteroids could be the precursors to meteoroid streams, clouds of dust and debris that eventually become meteor showers when they enter Earth's atmosphere. If this is true, then studying ultra-fast rotators might give us clues about where some of our most famous meteor showers come from. It could also help us predict future meteor showers by identifying which asteroids are currently shedding material. This leads to another question: could ultra-fast rotators be a hazard to spacecraft? If they are constantly throwing off debris, then any mission that gets too close could be at risk. Even tiny fragments traveling at high speeds could pose a major threat to delicate instruments. But beyond their dangers, ultra-fast rotators might also offer an opportunity. If they are actively shedding material, then we might not need to land on them at all to collect samples. Instead, we could send spacecraft to fly through the debris fields surrounding these asteroids, collecting particles as they are ejected. This would allow us to study their composition without the difficulty of dealing with their intense spin. Some missions have already tested similar techniques. NASA's OSIRIS-RX spacecraft, for example, used a contactless method to collect samples from the asteroid Bennu. A future mission could use similar technology to gather material from ultra-fast rotators, providing us with an unprecedented look at their makeup. Another intriguing possibility is that ultra-fast rotators could serve as natural accelerators for space travel. If a spacecraft could rendezvous with one of these rapidly spinning asteroids and attach a tether, it might be able to use the asteroid's spin to gain momentum. This concept, known as a momentum exchange tether, could allow for slingshot maneuvers that save fuel and provide a boost for deep space missions. Imagine a future where spacecraft use ultra-fast rotators as stepping stones, hitching rides from one asteroid to another, using their spin to propel themselves across the solar system. While this is purely speculative for now, the idea highlights just how much we still have to learn about these objects. And what about their origins? Could ultra-fast rotators be the remnants of ancient collisions, with their rapid spin being a sign of their violent past? Or could they be evidence of a completely unknown process in asteroid evolution? Some scientists speculate that these asteroids might have formed in regions of the solar system where intense gravitational interactions gave them their spin. Perhaps they originated in areas with strong tidal forces, such as near giant planets, before being ejected into their current orbits. Others believe that they might have acquired their spin through a slow but steady process known as the YORP effect. This occurs when sunlight unevenly heats an asteroid, causing thermal radiation to be emitted in a way that gradually increases its rotation over millions of years. If this effect is responsible for ultra-fast rotators, then it suggests that many more asteroids might eventually reach extreme spin rates given enough time. But could there be an even more exotic explanation? Some researchers have speculated that interactions with dark matter could play a role in the behavior of some asteroids. While this is highly speculative, it raises an interesting question. If ultra-fast rotators behave in ways that don't match our expectations, could it be a sign of physics we don't yet understand? It wouldn't be the first time that small objects in space have challenged our understanding of physics. Take Oumuamua, the first known interstellar object to pass through our solar system. It exhibited non-gravitational acceleration that some scientists struggled to explain. Could ultra-fast rotators be another puzzle piece in understanding how small bodies move and evolve in the cosmos? Some astronomers have even wondered if ultra-fast rotators could be artificial. While there is no evidence to suggest this, it's a thought-provoking idea. If an advanced civilization wanted to create a fast-spinning beacon in space, an asteroid would be a natural choice. A rapidly spinning object would stand out from the background, making it easy to detect from great distances. Of course, the more likely explanation is that ultra-fast rotators are entirely natural, but that doesn't make them any less fascinating. They are cosmic outliers, defying expectations and challenging our models of asteroid dynamics. They might hold the key to understanding how asteroids evolve over time, how material is transported across the solar system, and even how life's building blocks are distributed throughout the cosmos. But perhaps the biggest question of all is, how many of them are out there? If ultra-fast rotators are more common than we think, then they could represent a major population of small bodies that we have largely overlooked. There might be thousands, or even millions, of these extreme asteroids whirling through space, just waiting to be discovered. And what if some of them are on paths that bring them dangerously close to Earth? If we were to detect an ultra-fast rotator on a collision course with our planet, how would we stop it? A normal asteroid impact would already be catastrophic, but an impact from an ultra-fast rotator could be even worse. The rapid spin could cause unpredictable fragmentation, creating multiple impact points instead of just one. This is why understanding ultra-fast rotators isn't just about curiosity, it's about preparedness. The more we know about these objects, the better equipped we'll be to deal with any potential threats they might pose. But beyond their dangers, they represent one of the great cosmic mysteries still waiting to be unraveled. Each time we discover a new one, we are forced to reconsider what we thought we knew about asteroids, planetary formation, and the forces shaping our solar system. They remind us that space is still full of surprises, and that some of the strangest objects in the universe might be hiding in plain sight, spinning faster than we ever thought possible. Ultra-fast rotators push the boundaries of what we think is possible in asteroid physics. The sheer speed at which they spin suggests that either our understanding of asteroid composition is incomplete, or these objects have been shaped by forces we don't yet fully understand. If they truly are solid monolithic bodies, then their very existence tells us something crucial: not all asteroids follow the same rules. This could mean that many more undiscovered ultra-fast rotators are out there, waiting to challenge our assumptions. One major question is how these asteroids got to be this way. If their extreme spin is the result of the YRP effect, then it suggests that many asteroids could be on their way to becoming ultra-fast rotators given enough time. But if these objects formed this way from the beginning, then we need a new model to explain how certain asteroids develop in such an extreme manner. Consider the role of collisions. When asteroids collide, they can impart rotational energy to each other, but these impacts are typically chaotic and often lead to fragmentation. If an asteroid somehow managed to gain a massive amount of spin from a glancing impact, yet remained intact, it would be a rare event. Could it be that ultra-fast rotators are survivors of ancient, high-energy impacts that left them spinning like cosmic tops? Another possibility is that some ultra-fast rotators could be fragments of larger bodies that were once part of a more massive asteroid. If a parent body shattered due to a collision, it might have produced fragments that inherited an extreme rotation. However, this idea raises another issue. If these objects were once part of larger asteroids, why don't we see more of them? If fragmentation regularly produces ultra-fast rotators, we should be detecting a significant number of them. Perhaps their rarity is due to the fact that most asteroids simply can't survive spinning at such high speeds. If an asteroid begins to rotate too fast, the centrifugal forces will cause it to shed material, slowing its spin down over time. This means that ultra-fast rotators might be in a temporary phase of their evolution. Eventually, they will either break apart or lose enough mass to stabilize. This leads to another critical question. Are ultra-fast rotators evidence of an ongoing process of asteroid destruction? If these objects are constantly shedding material, then we might be witnessing asteroids actively disintegrating. Some could be in the final stages of their existence, with each spin cycle bringing them closer to complete breakup. If this is true, it might help explain the existence of certain meteoroid streams. When an asteroid sheds debris, that material can remain in space for long periods, forming a trail of particles that eventually enter Earth's atmosphere as meteor showers. This suggests that some of the most famous meteor showers could have originated from ultra-fast rotators in the past. This also raises an important question about planetary defense. If ultra-fast rotators are unstable and prone to shedding material, then their potential to create unpredictable debris fields could pose a threat to spacecraft or even Earth itself. If we were to detect one on a collision course with our planet, its rapid rotation could make deflection efforts much more complicated. Unlike a standard asteroid, which might be redirected with a kinetic impactor, an ultra-fast rotator could behave unpredictably under external forces. If its spin rate is affecting its structural integrity, then even a small change in momentum might cause it to fragment unpredictably. This means that any attempt to move an ultra-fast rotator away from Earth could result in it breaking apart and creating multiple smaller, but still dangerous, impactors. This is why understanding these objects is so important. They are not just rare curiosities. They could be key to understanding the dynamics of asteroid evolution, planetary defense, and even space resource utilization. If ultra-fast rotators contain unique materials or if their rapid spin makes them more accessible for mining, they could become targets for future space exploration missions. But what if ultra-fast rotators are even stranger than we think? Some scientists have speculated that their extreme rotation could be the result of interactions with forces we don't yet fully understand. Could tidal interactions with planets have played a role? Could they have once been part of a binary system where one object was ejected, leaving the remaining asteroids spinning rapidly? Or could they be interacting with dark matter in some way? While this is highly speculative, it raises an interesting point. If ultra-fast rotators display unexpected behavior that doesn't match our current models, then they might be signaling something we haven't yet discovered. It wouldn't be the first time that celestial objects have challenged our expectations. Throughout history, new astronomical discoveries have often forced us to rethink our understanding of the universe. From the discovery of exoplanets to the detection of interstellar visitors like Oumuamua, the cosmos continues to surprise us. Ultra-fast rotators might be yet another piece of that puzzle, hinting at deeper cosmic processes we have yet to fully grasp. If we want to truly understand ultra-fast rotators, we need more data. That means dedicating more telescopic observations to tracking their movements, measuring their compositions, and ideally, sending spacecraft to study them up close. If we could deploy a probe to one of these objects, we might be able to directly measure the forces at work, determine their structure, and test our theories about their formation. Some upcoming space missions might be able to provide partial answers. NASA's planned Near-Earth Object Surveyor, NEO Surveyor, mission will scan the sky for potentially hazardous asteroids, and it might detect more ultra-fast rotators in the process. The European Space Agency's Hera mission, which will study the asteroid Dimorphos after the DART impact, could also refine our understanding of asteroid behavior and stability. But until we can study ultra-fast rotators directly, they will remain one of the most intriguing unsolved mysteries of space. These objects are living contradictions, spinning too fast to exist, yet somehow persisting against the odds. They remind us that even in a universe we have studied for centuries, there are still phenomena that defy explanation. Every time we point our telescopes at the sky, we find new mysteries waiting to be solved. And among those mysteries, ultra-fast rotators stand out as some of the most perplexing. They challenge the limits of physics, hint at unseen forces, and keep astronomers on their toes, always searching for the next strange discovery hiding in the vastness of space. Ultra-fast rotators are not just an astronomical curiosity. They might hold the key to understanding some of the most fundamental aspects of how celestial bodies evolve. When an asteroid spins at extreme speeds, it challenges many of the conventional theories about how these objects form, survive, and eventually break apart. But the fact that they exist at all tells us something important. There are still unknown processes at work in space that we don't fully grasp yet. One of the biggest mysteries surrounding ultra-fast rotators is their internal structure. If they were loose piles of rubble, they would simply fly apart at the speeds they are spinning. So the fact that they remain intact strongly suggests that they are monolithic, or at least have a solid enough core to withstand extreme forces. This raises an interesting question. How do these asteroids form in such a way that they can resist centrifugal breakup? One theory is that ultra-fast rotators are actually fragments of larger parent bodies that were once part of bigger asteroids, or even protoplanets. When these parent bodies were shattered by massive collisions in the distant past, some of the fragments may have inherited extreme spin rates from the energy of the impact. If this is the case, then ultra-fast rotators might be remnants of ancient catastrophic events that shaped the early solar system. But even if they were formed from collisions, that still doesn't explain how they maintain their structure. If a fragment were rotating too quickly, it should still break apart unless it has a unique internal composition. Could it be that ultra-fast rotators are made of a much denser or stronger material than other asteroids? If so, what kind of material could withstand such forces? This question opens up an exciting possibility. If ultra-fast rotators are composed of denser materials, they could be hiding valuable resources that might be useful for space exploration. Some scientists have proposed that certain asteroids contain significant amounts of metals like nickel, iron, or even rare elements that are scarce on Earth. If ultra-fast rotators belong to this category, then they could become targets for future asteroid mining missions. Mining an ultra-fast rotator, however, would be an engineering challenge unlike any other. How do you land on something that is spinning so rapidly? If a spacecraft were to approach an ultra-fast rotator, it would have to match its rotation precisely or risk being flung away by the asteroid's centrifugal forces. Traditional landing techniques wouldn't work, so engineers would have to develop entirely new methods to anchor onto such an object. But beyond their potential for mining, ultra-fast rotators also raise an important issue for planetary defense. Most asteroid deflection strategies assume that a threatening asteroid can be nudged off course with a kinetic impactor or a gravity tractor. However, if an asteroid is spinning at extreme speeds, those methods might not work as expected. An impactor might hit an ultra-fast rotator and simply be deflected away, or worse, cause the asteroid to break into multiple high-speed fragments that could still be hazardous. This is why scientists need to study these asteroids more closely. The more we understand about their composition and behavior, the better prepared we will be to deal with any that pose a potential threat. Right now, our knowledge of ultra-fast rotators is limited to a handful of observations, but future missions might change that. If we could send a probe to one of these asteroids, we could gather direct measurements about its structure, rotation, and internal composition. One intriguing possibility is that some ultra-fast rotators could be ancient remnants of objects that formed outside our solar system. If an asteroid was ejected from another star system long ago and eventually made its way into ours, it might behave differently than typical solar system asteroids. Its spin rate, composition, or even surface features might be completely unlike anything we have seen before. Interstellar objects like Oumuamua and Borisov have already shown us that visitors from other star systems can look very different from the asteroids and comets we are familiar with. If some ultra-fast rotators are actually interstellar in origin, they might hold clues about the conditions in distant planetary systems. Studying them could give us a rare glimpse into the materials and processes that exist beyond our own cosmic neighborhood. Another strange possibility is that ultra-fast rotators might be undergoing a form of rotational evolution that we don't yet understand. Could there be an unknown force at work that is accelerating these objects over time? Some scientists have suggested that interactions with solar radiation, magnetic fields, or even dark matter might be influencing their spin rates in ways we haven't yet considered. While this is highly speculative, it wouldn't be the first time that astronomical discoveries have forced us to rethink our understanding of physics. Many scientific breakthroughs have come from studying objects that didn't behave the way we expected. Ultra-fast rotators might be a sign that there are still fundamental forces at play in space that we don't fully grasp yet. The next step in unraveling this mystery is simple: we need more data. Right now, only a small number of ultra-fast rotators have been identified, but that doesn't mean they are rare. There could be many more waiting to be discovered, hidden among the countless asteroids in our solar system. If telescopes and space missions can detect more of these objects, we might be able to figure out patterns in their distribution, spin rates, and compositions. For example, if ultra-fast rotators are mostly found in specific regions of the asteroid belt, that could tell us something about their origins. If they are more common in certain types of asteroid families, that might indicate that they formed through similar processes. And if some are discovered on trajectories that suggest they came from outside the solar system, that could be one of the most exciting findings in modern astronomy. But until we have more observations, ultra-fast rotators will remain one of the most puzzling and intriguing mysteries of space. They are objects that shouldn't exist, and yet they do. They defy our expectations, challenge our understanding of physics, and hint at deeper forces at work in the cosmos. One thing is certain: the more we learn about space, the more surprises it throws at us. Ultra-fast rotators are just one example of how much we still don't know. As our technology improves and our ability to explore the solar system expands, we will undoubtedly uncover even more strange and unexpected phenomena. Perhaps one day, a spacecraft will land on an ultra-fast rotator, drilling into its surface to reveal the secrets hidden beneath. Perhaps we will discover that these asteroids are made of materials we never expected, or that their spin rates are controlled by forces we have yet to understand. Until that day comes, they will remain one of the greatest unsolved riddles of our cosmic backyard. And who knows? Maybe the next time we look up at the sky, one of these rapidly spinning asteroids will be passing by, reminding us that even in the vast emptiness of space, there are still mysteries waiting to be uncovered. Ultra-fast rotators continue to challenge our understanding of the forces that shape asteroids and the broader dynamics of our solar system. One of the most pressing questions about these asteroids is, what is the upper limit of their spin rates? Is there a theoretical maximum speed beyond which no asteroid could possibly remain intact? So far, observations suggest that most asteroids larger than a few hundred meters in diameter have a spin rate slower than 2.2 hours per rotation. This is because rubble pile asteroids, which are loosely held together by gravity, would break apart if they spun any faster. However, ultra-fast rotators are much smaller, and many of them complete a full rotation in just a few minutes, or even seconds. For an object to spin this quickly without disintegrating, it must be held together by something other than just gravity. This is why astronomers believe that ultra-fast rotators are either monolithic, solid rock, or have some unknown cohesive force holding them together. Some scientists propose that electrostatic forces, van der Waals interactions, or even cohesive forces between tiny grains of material could help these objects resist centrifugal breakup. However, this leads to another mystery. If ultra-fast rotators are solid, how did they become that way? Most asteroids are thought to be the remnants of past collisions, but if an ultra-fast rotator was once part of a larger asteroid, how did it retain such a solid structure while everything else around it crumbled into loose debris? One possibility is that these asteroids underwent a process called sintering, where their materials fused together over time due to heat and pressure. This could have happened during their early formation when they were still part of larger bodies, or it could be a result of continuous exposure to space radiation and micrometeorite impacts. If this is the case, ultra-fast rotators might provide clues about how solid objects in space evolve over time. But what about the ones that didn't start as solid bodies? Could a rubble pile asteroid somehow transform into a monolithic one? Some researchers suggest that rapid rotation itself might play a role in reshaping these objects. If an asteroid starts spinning faster due to the YRP effect, a process where sunlight unevenly heats an asteroid and gradually changes its rotation, it could force the loosely bound material to either compact into a denser form or shed its outer layers, leaving behind only a hardened core. This could mean that ultra-fast rotators are not just unusual asteroids, but a stage in an evolutionary process that many asteroids go through. If so, studying them could help us understand how small bodies in space transition from one form to another over millions of years. Another strange aspect of ultra-fast rotators is their potential role in space weathering. Space is a harsh environment, constantly bombarding objects with cosmic rays, solar radiation, and micrometeorites. Over time, these forces can change the surface composition of asteroids, creating a weathered outer layer that is chemically different from the material underneath. Because ultra-fast rotators spin so quickly, they might experience unique weathering effects that don't occur on slower rotating asteroids. For example, if an ultra-fast rotator has a thin layer of dust or loose material on its surface, that material might not be able to stay attached due to the extreme rotation. Instead, it could be constantly flung off into space, exposing fresher, less weathered material underneath. If this is true, then ultra-fast rotators might appear different from other asteroids when observed with telescopes. Their surfaces might reflect light in unexpected ways, or they might lack the typical spectral signatures of weathered rock. Studying them in detail could provide insights into how space weathering affects different types of celestial bodies. But there's another possibility, one that's even stranger. Could some ultra-fast rotators actually be artificial? While this might sound like science fiction, there are real reasons to consider the idea. In recent years, astronomers have discovered objects in space that exhibit unusual motion patterns, leading to speculation that they could be artificial in origin. The interstellar object Oumuamua, for example, had an unexpected acceleration that some scientists struggled to explain with natural forces alone. If an ultra-fast rotator were an artificial object, perhaps a piece of long-lost space debris or even an ancient relic from an unknown civilization, its extreme spin could be a result of past interactions with other celestial bodies or even an intentional design feature. Of course, this idea remains purely speculative, but it raises an interesting point. If we ever do find evidence of extraterrestrial technology, it might not look like what we expect. Instead of giant spacecraft or massive structures, it could be small, fast-spinning objects that have been mistaken for natural asteroids. The only way to find out is to study ultra-fast rotators up close. Sending a spacecraft to one of these objects could provide definitive answers about their composition, structure, and origins. Future missions could use advanced imaging, spectroscopy, and even physical sampling to determine whether ultra-fast rotators are simply extreme examples of natural asteroids or something more mysterious. Until then, they remain one of the most puzzling enigmas of our solar system. These tiny, rapidly spinning objects shouldn't exist according to our current understanding, yet they do. They challenge what we know about asteroid formation, planetary defense, and even the nature of celestial bodies themselves. Ultra-fast rotators serve as a reminder that space is far from fully explored. For every mystery we solve, new questions emerge, pushing the boundaries of our knowledge and forcing us to rethink what we thought we understood about the universe. Ultra-fast rotators are a reminder that space is full of surprises. They force us to question our assumptions about how celestial bodies behave and what limits nature imposes. If these tiny asteroids can defy expectations, what else in our universe might be capable of similar anomalies? Could there be even smaller objects spinning even faster, beyond what our current instruments can detect? One of the biggest challenges in studying ultrafast rotators is their sheer size. Many of them are only a few meters across, making them difficult to observe with ground-based telescopes. Even when they are detected, gathering detailed information about their shape, composition, and surface features is incredibly difficult. To overcome this, astronomers use a technique called light curve analysis. When an asteroid spins, the amount of light it reflects changes depending on its shape and orientation. By carefully measuring these changes, scientists can determine an asteroid's rotation speed and sometimes even infer its shape. However, light curve analysis has its limitations. If an ultrafast rotator is unusually shaped, say, if it's elongated like a cigar or irregularly jagged, it can create complex light patterns that are hard to interpret. Additionally, if an asteroid is covered in material that reflects light unevenly, it can create misleading data, making it difficult to determine its true structure. This is where radar observations come into play. By bouncing radio waves off an asteroid and analyzing how they return, astronomers can create more detailed images of its surface and rotation. Some of the most detailed images of asteroids ever captured have come from planetary radar systems, such as those at Arecibo, before it collapsed, and the Goldstone Deep Space Communications Complex. Despite these efforts, ultra-fast rotators remain some of the most elusive objects in the solar system. Their small size means that they often go unnoticed until they pass close to Earth. When they do, astronomers have only a short window of time to study them before they move out of range. One of the most intriguing questions is whether these asteroids are common or rare. Are we only detecting a small fraction of a much larger population? If so, where are the rest hiding? It's possible that many ultra-fast rotators exist in regions of space where our telescopes have difficulty detecting them. Some might reside in the asteroid belt, where their rapid motion makes them blend in with slower-moving objects. Others might be scattered throughout the solar system, traveling on paths that rarely bring them close to Earth. One theory suggests that ultra-fast rotators might be remnants of larger asteroids that broke apart in violent collisions. If a massive impact shattered an asteroid into smaller fragments, the resulting debris could inherit a wide range of spin rates. Some pieces might tumble chaotically, while others could be set spinning at extreme speeds. If this is the case, then studying ultra-fast rotators could give us insights into the history of asteroid collisions and the forces that shape our solar system. It could also help us understand how planetary bodies form and evolve over time. There's another possibility, one that challenges traditional thinking about how asteroids behave. Could some ultra-fast rotators be actively accelerating? At first, this idea might seem impossible. In space, an object in motion tends to stay in motion unless acted upon by an external force. However, there are mechanisms that could cause an asteroid's spin rate to increase over time. One of the most well-known is the YORP effect, which occurs when sunlight strikes an asteroid unevenly. If an asteroid has an irregular shape, certain areas absorb more sunlight than others. As the absorbed heat is re-emitted, it creates tiny forces that, over long periods, can change the asteroid's rotation speed. In most cases, the YRP effect is a slow process, taking thousands or even millions of years to produce noticeable changes. But what if some ultra-fast rotators are experiencing an accelerated version of this effect? Could they be spinning up at a much faster rate than expected? If so, it would suggest that some asteroids are far more dynamic than we thought. Instead of being passive chunks of rock drifting through space, they might be actively evolving, their rotation speeds constantly shifting due to the subtle forces acting upon them. This raises an even more startling question. What happens if an ultra-fast rotator spins too fast? There is a theoretical limit to how fast an asteroid can rotate before it breaks apart. If an object's spin rate exceeds this critical threshold, the centrifugal forces at its equator become stronger than the gravitational or cohesive forces holding it together. When this happens, material starts to fly off, creating a debris cloud that can either escape into space or form a temporary ring around the asteroid. Some astronomers believe that ultra-fast rotators might be actively shedding material in this way. If this is true, then these asteroids could be a key part of the process that creates meteoroid streams, clouds of dust and debris that eventually fall to Earth as meteor showers. In other words, when you see a shooting star streak across the night sky, there's a chance that it came from an ultra-fast rotator that spun itself apart millions of miles away. But what if an ultra-fast rotator doesn't just lose small amounts of material? What if it undergoes a catastrophic breakup? If an asteroid were to reach an extreme spin rate and fully disintegrate, the resulting explosion could scatter debris across a vast area. In some cases, the fragments might remain in loosely bound clusters, forming asteroid families that travel together through space. This process could explain why some asteroid families appear to have unusual rotation properties. If they originated from ultra-fast rotators that broke apart, their fragments might still retain some of the original spin energy, leading to rapid and unpredictable rotation rates. It's also possible that some ultra-fast rotators have already met their fate, breaking apart before we ever had a chance to observe them. If this is the case, then there may be a hidden population of destroyed ultra-fast rotators whose remnants are scattered throughout the solar system. Another mystery is whether ultra-fast rotators could pose a threat to Earth. While most are small and unlikely to survive entry into our atmosphere, larger ones could cause significant damage if they were to collide with our planet. Fortunately, their rapid spin rates might actually make them less dangerous. If an ultra-fast rotator were on a collision course with Earth, there's a good chance that it would break apart before impact, reducing the potential damage. However, this isn't always a guarantee. Some fast-spinning asteroids could hold together long enough to reach the surface. Understanding their structural integrity is crucial for planetary defense. If we ever need to deflect an incoming asteroid, knowing whether it is a solid monolith or a loosely bound pile of rubble could determine the best approach. Some scientists have suggested that if an ultra-fast rotator were heading toward Earth, it might be possible to speed up its spin even further, causing it to self-destruct before impact. This could be done using targeted energy sources like lasers or kinetic impactors, but the feasibility of such methods remains uncertain. Ultimately, ultra-fast rotators represent one of the great unsolved mysteries of our solar system. They challenge our understanding of how small celestial bodies form, evolve, and interact with their environment. Their existence raises fundamental questions about the nature of asteroids, the forces that shape them, and the hidden processes at work in deep space. Perhaps the most exciting possibility is that ultra-fast rotators are not just isolated oddities but part of a larger, yet undiscovered class of celestial objects. If so, then studying them could open the door to a new era of asteroid science, revealing secrets that have remained hidden for billions of years. The search for answers continues, but one thing is clear: ultra-fast rotators are far more than just spinning rocks. They are cosmic enigmas, pushing the limits of what we thought was possible in the vast, ever-changing expanse of space. One of the most fascinating aspects of ultra-rapidly spinning asteroids is the sheer variety in their possible compositions. Most asteroids in the solar system fall into one of three major categories: C-type, carbonaceous; S-type, silicaceous; and M-type, metallic. The composition of an asteroid significantly affects its structural integrity, and for ultra-fast rotators, This can mean the difference between stability and complete disintegration. C-type asteroids, which are the most common, are made primarily of carbon-rich material mixed with silicates. These asteroids are often relatively fragile, held together by weak gravitational and cohesive forces. If an ultra-fast rotator belongs to this category, it is likely to be highly porous and at constant risk of shedding material due to its high spin rate. S-type asteroids are composed of silicate rock and small amounts of metal. They are typically more rigid than C-types, which might allow some of them to spin faster without breaking apart. However, their internal structure can vary greatly. Some may be solid monoliths, while others might be loose collections of smaller rocks held together by weak forces. M-type asteroids are the most structurally sound. These asteroids contain high amounts of metal, making them far denser and less likely to disintegrate under extreme rotational forces. Some scientists believe that the fastest spinning asteroids are likely metallic because they can withstand the stress of high rotation speeds better than their rocky or carbonaceous counterparts. This raises an interesting possibility. Could some ultra-fast rotators be made almost entirely of metal, remnants of ancient planetary cores that were shattered by cosmic collisions? If so, they could provide insights into the early formation of planets and the distribution of metals in the solar system. Another key factor in an asteroid's ability to withstand ultra-fast rotation is its shape. While we often picture asteroids as irregular, potato-like objects, many ultra-fast rotators exhibit surprisingly uniform shapes. Some appear nearly spherical, while others resemble flattened disks or elongated ellipsoids. Why does shape matter? Because the way an asteroid's mass is distributed affects how it handles rotational forces. A perfectly symmetrical asteroid might be able to spin faster without experiencing uneven stresses, whereas an irregularly shaped one could develop weak points that eventually lead to fragmentation. This is why many of the fastest rotating asteroids tend to be relatively small. Larger asteroids, especially those with irregular shapes, are more prone to structural failure when subjected to extreme spin rates. The smaller the asteroid, the easier it is for cohesive forces, such as van der Waals forces, to hold it together despite rapid rotation. Some ultra-fast rotators exhibit an even stranger characteristic. They seem to be oblate spheroids, meaning they are slightly squashed due to their rapid rotation. This suggests that their own spin is reshaping them, causing material to migrate toward the equator, gradually changing their overall form over time. This leads to another mystery. Could some ultra-fast rotators eventually evolve into entirely new types of celestial bodies? If an asteroid spins fast enough for long enough, could it stretch itself into a new, previously unknown shape? And if so, what implications would that have for our understanding of how small bodies evolve in the solar system? One of the most intriguing theories about ultra-fast rotators is that they might be responsible for some of the most unusual asteroid phenomena we've observed. For example, astronomers have discovered asteroids with rings, thin, icy structures encircling the main body, similar to miniature versions of Saturn. Could these rings have formed as a result of material being ejected from ultra-fast rotators? If an asteroid spins too quickly, loose debris on its surface could be flung outward into orbit, forming a temporary ring. Over time, these rings could either disperse into space or coalesce into small moons. This could explain why some asteroids, like 10199 Chariklo and 2060 Chiron, have been observed with ring systems despite their relatively small size. There's also the question of asteroid pairs, two asteroids that orbit each other in close proximity. Some asteroid pairs appear to have formed when a single asteroid spun so fast that it split into two pieces. If this is the case, then ultra-fast rotators might be the key to understanding how binary asteroids come into existence. But what happens when an ultra-fast rotator reaches the ultimate limit of its spin? While some simply shed material gradually, others might undergo catastrophic breakups, shattering into multiple fragments. Some of these fragments may remain gravitationally bound, forming asteroid clusters, while others could become independent bodies, creating entirely new populations of small asteroids. This raises another question. Could ultra-fast rotators be responsible for some of the meteoroids that occasionally strike Earth? If a rapidly spinning asteroid were to break apart, its fragments might follow new trajectories, eventually entering Earth's atmosphere as meteors. Some meteor showers, such as the Geminids, are believed to be linked to asteroid activity rather than comets. Could ultra-fast rotators be playing a hidden role in these cosmic events? Recent studies have suggested that some ultra-fast rotators might also experience internal deformation. If an asteroid is spinning at extreme speeds, the stress within its core could cause gradual shifts in its internal structure. This could lead to seismic activity, surface cracking, and even the gradual migration of material from one part of the asteroid to another. This means that ultrafast rotators aren't just static objects. They might be constantly evolving, changing shape, and even reorganizing their internal structures over time. This makes them fundamentally different from the slow-spinning asteroids that dominate the main belt. But how do ultra-fast rotators even form in the first place? The simplest explanation is collisions. When two asteroids collide, the energy of the impact can impart spin to the resulting fragments. If the collision is particularly violent, some of these fragments might inherit extreme rotational speeds, turning them into ultra-fast rotators. However, not all ultrafast rotators show signs of being recent impact fragments. Some appear to have been spinning rapidly for millions, or even billions of years. This suggests that other forces must be at play, forces that can gradually increase an asteroid's spin rate over time. One of these forces is the YRP effect, which we discussed earlier. But could there be other, more mysterious mechanisms at work? Some scientists have speculated that interactions with solar wind and magnetic fields could also influence an asteroid's rotation. If an asteroid is metallic, it could respond to electromagnetic forces in space, potentially altering its spin rate in ways we don't yet fully understand. Another possibility is tidal interactions with planets. If an asteroid passes close to a massive planet like Jupiter, the gravitational forces could exert torques that gradually change its rotation speed. This could explain why some ultrafast rotators appear to be on unusual orbits, suggesting past encounters with giant planets. Even more intriguing is the idea that some ultrafast rotators might not be natural at all. What if some of them were artificially altered, perhaps by extraterrestrial civilizations? While this might sound like science fiction, it's not entirely implausible. Some scientists have speculated that intelligent civilizations, if they exist, might use small asteroids as spacecraft or probes. If such objects were deliberately set spinning for stabilization or propulsion purposes, they might appear as ultrafast rotators when observed from Earth. Of course, there is no direct evidence for this theory, but it raises an interesting point. What if ultrafast rotators are not just natural anomalies, but clues to hidden processes we haven't yet discovered? The more we learn about ultrafast rotators, the more questions arise. How many of them exist? Are they truly rare, or have we only scratched the surface? Could some of them be undergoing transformations we've never imagined? The mystery continues to deepen, and with each new discovery, we edge closer to unraveling the secrets of these bizarre, rapidly spinning celestial objects. Ultra-rapidly spinning asteroids push the boundaries of what we thought was possible for small celestial bodies. Their extreme spin rates defy conventional understanding of asteroid physics, forcing scientists to rethink what we know about the strength, structure, and evolution of these objects. The deeper we investigate, the more we realize that these asteroids might be at the forefront of some of the most puzzling processes in the solar system. One of the biggest mysteries surrounding ultra-fast rotators is their internal structure. Are they solid monoliths, held together by sheer material strength? Or are they rubble piles, barely held together by weak forces? The answer to this question determines whether these asteroids can maintain their insane rotation speeds indefinitely or if they are doomed to eventual destruction. Traditional models of asteroid formation suggest that most small asteroids are not single, solid rocks but rather loosely bound collections of debris. This rubble pile structure results from billions of years of collisions and reaccumulation. These bodies are held together by gravity and weak cohesive forces, which should theoretically make them highly vulnerable to high-speed rotation. If this were the case, any ultra-rapidly spinning asteroid made of rubble would tear itself apart. But some ultra-fast rotators have been observed to maintain their structure despite their extreme spin. This suggests that at least some of these asteroids must be solid monoliths, objects made of a single, unbroken mass of rock or metal. These rare monoliths would have to be incredibly strong to resist the forces trying to pull them apart, leading scientists to believe that they could be remnants of planetary cores or large impact fragments that never broke apart further. This raises another intriguing possibility. Could some of these asteroids be leftovers from the very early solar system, pieces of protoplanetary material that have remained unchanged for billions of years? If so, ultra-fast rotators could be some of the oldest, most pristine objects in the solar system, offering a window into the conditions that existed when planets were first forming. But if most asteroids are rubble piles, how do some of them manage to spin so fast without disintegrating? One answer might lie in cohesive forces at the microscopic level. Even if an asteroid is made of loosely bound material, tiny electrostatic and molecular forces, similar to those that allow sand grains to stick together, could help hold it intact. This theory suggests that some ultra-fast rotators might not be purely solid, but instead consist of material that has bonded together over time due to space weathering and thermal effects. Speaking of space weathering, the constant exposure to cosmic radiation, solar wind, and micrometeorite impacts could be playing a role in how ultra-fast rotators evolve. Over time, these processes could alter the surface composition, creating a hardened outer shell that acts as a protective layer. This shell could allow an otherwise weak asteroid to maintain an extreme rotation rate for longer than expected before eventually succumbing to internal stresses. This could also explain why some ultra-fast rotators appear to have unusually smooth surfaces. While most asteroids are covered in craters, dust, and loose debris, some rapidly spinning asteroids seem to lack these features. One possibility is that their extreme spin rates have caused surface material to be ejected, leaving behind only the most stable and tightly bound material. Another major mystery is how these asteroids get up to such extreme speeds in the first place. While we've discussed the YRP effect as one possible explanation, could there be other forces at play? Some scientists have suggested that ultra-fast rotators might be the result of past near-miss encounters with planets. If an asteroid passed close enough to a planet like Earth or Jupiter, tidal forces could impart a spin boost, accelerating the asteroid to its current extreme speed. There is also the possibility that some ultra-fast rotators gain their high spin rates from binary asteroid interactions. If a small asteroid was once part of a binary system, two asteroids orbiting each other, it might have gained rotational energy from its companion before eventually separating. This could explain why some ultra-fast rotators appear to have unusual orbits that don't match typical asteroid belt trajectories. Adding to the mystery is the fact that some of these asteroids seem to defy predictions about their structural limits. Based on current models, asteroids spinning above a certain rate should be flinging material off their surfaces or breaking apart entirely. But instead, some ultra-fast rotators appear to be stable for long periods. This suggests that we might not fully understand the strength and resilience of asteroid material at the microscopic level. If ultra-fast rotators are capable of maintaining their speeds for millions of years, what eventually happens to them? Do they gradually slow down due to space dust drag and thermal radiation? Or do they continue spinning until they eventually reach a point of catastrophic breakup? The answer to this question could help us understand asteroid lifetimes and predict future asteroid behaviors. One thing is certain: studying ultra-rapidly spinning asteroids isn't just an academic curiosity. It has real-world implications. Understanding these asteroids could help us develop better asteroid impact prediction models, improve our ability to detect potentially hazardous objects, and even aid in future asteroid mining efforts. If some ultra-fast rotators turn out to be rich in metals, they could become prime candidates for future space mining missions. Extracting valuable resources from asteroids is a concept that has been gaining interest in recent years, with several private companies and space agencies exploring the possibility. But mining an asteroid spinning at extreme speeds would be an engineering challenge unlike anything we've faced before. The more we learn about ultra-fast rotators, the more we realize just how little we truly know about them. Are they a rare anomaly, or are they more common than we think? Could they be revealing hidden forces in the solar system that we haven't yet identified? Every new discovery about these objects only raises more questions. The mystery of ultra-rapidly spinning asteroids is far from solved, and as technology improves, we may finally get the answers we need. But for now, they remain some of the most bizarre, intriguing, and unexplained objects in the universe. The study of ultra-rapidly spinning asteroids isn't just a fascinating academic pursuit, it holds the key to understanding some of the fundamental processes shaping our solar system. These asteroids are unlike anything we typically see, defying expectations about how small bodies should behave in space. Their extreme spin rates challenge our understanding of structural integrity, surface dynamics, and the forces that shape celestial objects over time. The deeper we look, the more we realize these asteroids might be rewriting the rules of planetary science. One of the most perplexing questions about ultra-fast rotators is their longevity. If an asteroid is spinning so fast that it's on the verge of breaking apart, how long can it maintain this state before succumbing to the forces acting on it? Some scientists believe that many ultra-fast rotators are temporary objects, asteroids that have only recently gained their extreme spin rates due to external influences. If this is true, they could represent a short-lived phase in an asteroid's evolution, providing us with a rare glimpse into a process that usually goes unnoticed. But if ultra-fast rotators are common and persist for long periods, that would suggest that small asteroids are far stronger than previously thought. In that case, the implications would be profound, as it would mean our current models of asteroid composition and fragmentation might need to be revised. Could some of these asteroids be composed of exotic materials that allow them to withstand incredible stress? Are they the remnants of planetary collisions, formed under conditions that gave them unusual strength? Or do they possess some unknown internal reinforcement that prevents them from flying apart? One possibility is that the internal structure of these asteroids is far more complex than we currently assume. While most asteroids are thought to be either solid monoliths or loosely bound rubble piles, ultra-fast rotators might have internal reinforcement due to their unique formation history. Some scientists suggest that rapid spin could cause material inside the asteroid to compact over time, creating a dense, tightly packed core that helps maintain structural integrity. Another theory is that rapid rotation itself could generate forces that counteract disintegration. If an asteroid is spinning fast enough, centrifugal forces might push material outward, creating a sort of equilibrium where the forces pulling the asteroid apart are balanced by the internal cohesion holding it together. This could explain why some ultra-fast rotators appear to be stable despite exceeding the theoretical spin limit. But what happens when an asteroid finally reaches the breaking point? Scientists suspect that when an ultra-fast rotator reaches its maximum spin speed, it undergoes one of two possible fates. It could shed material from its surface in small amounts over time, gradually losing mass and slowing down as a result. This could explain why some asteroids appear to have smooth surfaces, as any loose material would have been ejected long ago. Alternatively, the asteroid could experience a catastrophic breakup event, splitting into multiple fragments that then go on to form their own independent bodies. This would suggest that ultra-fast rotators play a significant role in the creation of small asteroids, contributing to the overall population of near-Earth objects. In this scenario, studying these asteroids could help us understand how asteroid families form and how space debris is distributed throughout the solar system. Interestingly, some observations suggest that asteroid breakups caused by rapid rotation might not always be violent. Instead of shattering into countless pieces, some asteroids may undergo a more gradual fission process, where material is slowly pulled away, forming a secondary object that orbits the original asteroid. This could explain why some binary asteroid systems appear to have unusual rotation patterns, as they may have originated from a single ultra-fast rotator that split apart. If ultra-rapidly spinning asteroids are capable of breaking apart in this way, it raises an important question. Could this process be responsible for some of the asteroid pairs and small moonlets that we see in the solar system? Many asteroids have tiny companions orbiting them, and while some of these moons are thought to have formed through collisions, others may have been created through rotational fission. Another area of interest is how ultra-fast rotators interact with their environment. If an asteroid is spinning at extreme speeds, could that affect how it absorbs and emits heat? The YRP effect, which causes asteroids to change their spin rates over time due to uneven thermal radiation, is already known to influence slow-spinning asteroids. But for ultra-fast rotators, the effect might be amplified, leading to even more dramatic changes in spin over shorter timescales. If these asteroids are absorbing heat in unusual ways, that could also impact their surface composition. Some researchers speculate that rapid rotation could cause volatile materials to be ejected from the surface more easily, potentially creating a different chemical profile compared to slower spinning asteroids. If true, ultra-fast rotators might offer a unique opportunity to study how asteroid surfaces evolve under extreme conditions. Despite everything we've learned about these bizarre objects, many fundamental questions remain unanswered. For instance, are ultra-fast rotators a common stage in asteroid evolution, or are they rare anomalies? Do they eventually slow down and become ordinary asteroids, or do they always end in destruction? And if some of them do break apart, what determines whether they form new binary systems or simply disintegrate? One of the biggest challenges in studying ultra-fast rotators is that they are incredibly difficult to observe. Because they are small and spin so rapidly, they often appear as mere points of light in telescopes, making it hard to gather detailed data about their composition and structure. Advanced observational techniques, such as radar imaging and space-based telescopes, are helping scientists get a clearer picture, but there is still much we don't know. Future space missions could provide crucial insights into these asteroids. If a spacecraft were to visit an ultra-fast rotator up close, it could answer many of the pressing questions about their composition, internal structure, and rotational behavior. Even a brief flyby mission could provide valuable data, revealing details that are impossible to see from Earth. Some researchers have even proposed the idea of deliberately spinning up an asteroid to see what happens. By using controlled forces, such as a small impact or a targeted spacecraft maneuver, we could artificially accelerate an asteroid's rotation and observe the effects in real time. This kind of experiment could help confirm theories about rotational breakup and give us a better understanding of the limits of asteroid stability. As our technology improves, we may finally be able to unravel the mysteries of ultra-fast rotators. These asteroids challenge our understanding of physics, materials science, and planetary evolution, making them one of the most intriguing subjects in modern astronomy. They force us to question what we thought we knew about the strength and resilience of celestial bodies, and they may hold clues to deeper mysteries about the formation and evolution of the solar system. Ultra-rapidly spinning asteroids are a testament to the fact that the universe is far stranger and more complex than we ever imagined. They defy expectations, challenge our theories, and continue to surprise us with their seemingly impossible behavior. And as we continue to study them, we may discover that they are just the beginning of an even larger and more perplexing mystery, one that could reshape our understanding of the cosmos itself. Ultra-rapidly spinning asteroids are some of the strangest objects in our solar system, and their extreme behavior forces us to reconsider what we think we know about celestial mechanics. When an asteroid spins at such an incredible rate, its surface experiences forces that are unlike anything found on Earth. Gravity still plays a role, but centrifugal force becomes a dominant factor, meaning that any loose material on the asteroid's surface is constantly being pulled outward. This could explain why some of these asteroids appear unusually smooth. Any loose rocks or dust might have already been flung into space. But what about the larger fragments? If an asteroid is spinning at an extreme rate, could it be shedding material in a way that creates entirely new objects? This is where the idea of rotational fission comes into play. Scientists believe that if an ultra-fast rotator reaches a critical speed, it could begin splitting apart, ejecting fragments that might eventually become their own independent asteroids. This process could help explain why some asteroids appear to be paired with smaller moonlets that orbit them. These secondary bodies may have originally been part of a single fast-spinning asteroid that broke apart due to excessive rotation. One of the most exciting implications of this idea is that ultra-rapidly spinning asteroids might actually be responsible for seeding space with new asteroid families. Instead of being rare, temporary objects that eventually break apart, they could be an important part of the natural cycle of asteroid formation. If true, This would mean that many of the small asteroids we see today might have originated as fragments from once faster spinning parent bodies. This idea also leads to another interesting question. Could this process be happening right now? If some asteroids are spinning so fast that they are constantly shedding material, then it's possible that new asteroids are forming all the time. Scientists have already detected cases where asteroids appear to have split apart within the last few decades or centuries. On cosmic timescales, that's practically a blink of an eye. Some of these newly formed asteroids might even still be in the process of settling into their final shapes and orbits. But if ultra-fast rotators are constantly losing material, how do they maintain their incredible spin rates? This is where external forces come into play. One of the biggest influences on an asteroid's rotation is the YRP effect, a process in which sunlight heats an asteroid's surface unevenly, causing it to slowly change its spin over time. For many asteroids, this effect gradually increases their rotation speed until they reach a critical point, at which they either break apart or undergo some kind of internal reorganization to stabilize themselves. The YRP effect is particularly interesting because it suggests that ultra-fast rotators aren't necessarily born spinning at extreme speeds. Instead, they might start out as slower spinning asteroids that are gradually accelerated by the energy from the Sun. Over thousands or even millions of years, an asteroid can be spun up to incredible speeds by nothing more than the subtle pressure of thermal radiation. This means that ultra-fast rotators might not be a special category of asteroids, but rather a natural stage in the life cycle of many small celestial bodies. However, not all ultra-fast rotators are created equal. Some of them spin so fast that they seem to defy known physical limits, leading scientists to wonder if they might contain exotic materials or unusual internal structures. Could some of these asteroids have cores that are far denser or more resistant to stress than we expect? Or could their rapid spin be the result of unique formation processes that we don't yet understand? There's also the possibility that some ultra-fast rotators are actually the result of high-speed collisions. When two asteroids crash into each other at high velocity, the resulting debris can be flung into space with incredible force. If a fragment from such a collision is small and irregularly shaped, it could inherit a rapid spin from the impact. Some scientists believe that certain ultra-fast rotators might be the leftover remnants of violent asteroid collisions, with their extreme spin rates serving as evidence of their chaotic origins. This idea is particularly intriguing because it suggests that ultra-fast rotators could be among the youngest asteroids in the solar system. If their spin rates are a direct result of recent collisions, then some of these objects might have formed relatively recently on geological timescales. Studying them could give us a unique window into the ongoing processes that shape our solar system, allowing us to observe the aftermath of asteroid impacts in real time. But not all ultra-fast rotators are likely to be recent arrivals. Some may have been spinning rapidly for millions, or even billions, of years. If this is the case, then it raises another critical question: how have they managed to survive for so long without breaking apart? One possibility is that they have undergone a process of self-reinforcement, where their rapid spin has caused their internal material to become more compact over time. If an asteroid is constantly spinning, the centrifugal forces acting on it could gradually rearrange its interior, squeezing loose material into a denser, more cohesive structure. This would mean that some ultra-fast rotators might actually become stronger as they continue spinning. Instead of being fragile, temporary objects that are destined to break apart, they could be incredibly stable structures that have found a way to resist the forces acting upon them. If true, this would suggest that some of these asteroids could remain in their extreme spin states for incredibly long periods, potentially outlasting even some of the larger, slower-moving asteroids in the solar system. Of course, not every ultra-fast rotator is going to be lucky enough to achieve this level of stability. Many of them are likely to reach a point where they can no longer hold themselves together, leading to sudden and dramatic breakup events. When an ultra-fast rotator finally exceeds its structural limits, it could send debris flying in all directions, creating a miniature asteroid field that spreads out over time. Some of this debris might eventually fall into orbits around larger asteroids, forming new moonlets or secondary bodies that continue to orbit their parent objects. This idea also has implications for planetary defense. If an ultra-fast rotator were to break apart near Earth, the resulting debris could pose a significant impact risk. While individual fragments might be small, a breakup event could produce a swarm of asteroid pieces that would be difficult to track and predict. Understanding the behavior of ultra-fast rotators is therefore not just a matter of scientific curiosity. It's also an important step toward improving our ability to detect and mitigate potential asteroid threats. Scientists are currently using a combination of telescopic observations, radar imaging, and computer simulations to study these asteroids in more detail. However, the best way to truly understand them would be to send a spacecraft to observe one up close. A dedicated mission to an ultra-fast rotator could provide critical insights into its surface composition, internal structure, and rotational dynamics, answering many of the questions that are still unresolved. Some researchers have even proposed the idea of attempting to alter an ultra-fast rotator's spin rate using controlled experiments. By applying external forces, such as a small impact or a controlled burst of gas, it might be possible to slow down or speed up an asteroid's rotation in a way that allows scientists to directly observe the effects. Such an experiment could be invaluable for testing theories about asteroid stability and rotational breakup, potentially leading to new insights into the physics of small celestial bodies. As technology advances, our ability to study and interact with asteroids will continue to improve. Future missions may not only observe ultra-fast rotators but also attempt to manipulate them, providing a new level of control over these mysterious objects. Whether through robotic probes, sample return missions, or even experimental asteroid deflection techniques, the study of ultra-rapidly spinning asteroids is poised to become one of the most exciting frontiers in planetary science. These asteroids are a reminder that the universe is still full of surprises. They challenge our expectations, defy our predictions, and force us to reconsider what we think we know about the nature of celestial bodies. And as we continue to study them, we may discover that they hold the key to unlocking even deeper mysteries about the evolution of our solar system and the forces that shape the cosmos. Ultra-rapidly spinning asteroids are not just scientific curiosities. They represent a puzzle that stretches our understanding of physics, celestial mechanics, and even the long-term stability of objects in space. The fact that some of these asteroids can spin so fast without disintegrating suggests that they are not as fragile as we might assume. In many cases, their extreme spin rates may indicate a highly compacted, possibly monolithic structure rather than a loosely bound, rubble pile formation, which is common among many other asteroids. This difference is important because it helps scientists categorize asteroids based on their structural integrity. The term, rubble pile, refers to asteroids that are essentially collections of boulders and dust held together loosely by gravity. These types of asteroids are common, and they can be disrupted relatively easily by external forces such as collisions, or the YORP effect gradually spinning them apart. But ultra-fast rotators behave differently. If they were rubble piles, their extreme spin should tear them apart almost immediately. The fact that they survive suggests that they may be more solid than previously thought. The implications of this go beyond just understanding asteroid composition. If some ultra-fast rotators are monolithic, meaning they are single, solid rock structures, then they could be far older than previously estimated. Unlike rubble pile asteroids, which may form from the remnants of past collisions, monolithic asteroids could be leftover building blocks from the early solar system. In other words, they may be among the oldest objects in existence, providing a direct link to the conditions present when planets were still forming. One major question that arises from this is, how did these objects survive in such a hostile environment for billions of years? Space is not a quiet place. Asteroids frequently collide with one another, experience temperature changes, and are constantly bombarded by cosmic radiation. Yet, somehow, ultra-rapidly spinning asteroids persist, even with spin rates that should theoretically tear them apart. Some scientists believe that this could be due to their composition. If an asteroid is made of a particularly strong type of rock or metal, it may be able to resist the centrifugal forces that would otherwise destroy it. This theory is supported by observations of certain ultra-fast rotators that reflect light in a way that suggests a metallic composition. If these asteroids are indeed made of metal, they might be the remnants of ancient planetary cores, fragments of larger celestial bodies that were shattered in past cosmic collisions. The idea that some of these asteroids could be metallic opens up fascinating possibilities. If ultra-fast rotators are rich in metals such as iron, nickel, and even rare elements like platinum or gold, they could be prime candidates for future asteroid mining missions. Many space agencies and private companies are already considering the economic potential of asteroid mining, and ultra-fast rotators might turn out to be some of the most valuable targets. But mining an ultra-fast rotator would be incredibly challenging. Their high spin rates make it difficult to land a spacecraft safely. Any attempt to interact with the surface of one of these asteroids would need to account for the fact that loose material is likely being flung outward at high speeds. Traditional drilling methods would not work in such an environment, so engineers would need to develop entirely new techniques for anchoring onto the surface and extracting materials. Even if mining is not the immediate goal, sending a mission to study an ultra-fast rotator up close would be an invaluable scientific endeavor. The more we learn about these extreme objects, the better we will understand the physics governing small bodies in space. If we can determine why some of these asteroids can spin so fast without breaking apart, we might unlock new insights into the strength and composition of celestial bodies across the solar system. Another intriguing possibility is that some ultra-fast rotators could be temporarily stable rather than permanently so. In other words, they might not remain in their extreme spin states forever. Over time, various forces, including gravitational interactions with other bodies, the continued influence of the YRP effect, or minor collisions, could gradually slow them down. If this is the case, then some of the ultra-fast rotators we see today might eventually settle into more normal spin rates, losing their extreme status. However, there is also the possibility that some of these asteroids will eventually reach a breaking point. If their spin rates continue to increase due to external forces, they may eventually cross the threshold where they can no longer hold together. When this happens, they could undergo a catastrophic breakup event, scattering debris across space. These events might be rare, but they could contribute to the formation of asteroid families, groups of asteroids that share a common origin. This could also help explain why we sometimes observe active asteroids, which exhibit comet-like behavior despite being classified as asteroids. Some scientists believe that at least some of these active asteroids might actually be ultra-fast rotators that have begun shedding material due to their extreme spin rates. In some cases, the debris being ejected could create a temporary tail, making them resemble comets. The study of ultra-rapidly spinning asteroids is still in its early stages, and many questions remain unanswered. But one thing is clear: these objects are not just anomalies. They are key pieces of the puzzle when it comes to understanding the solar system's evolution. Their existence challenges our assumptions about what asteroids can be and how they behave over long periods of time. As our technology advances, we may soon be able to observe these asteroids in greater detail. Missions equipped with advanced imaging techniques, spectrometers, and even landers could reveal exactly what these objects are made of and how they manage to maintain their rapid spins. In the future, we might even develop ways to slow down or manipulate their rotation artificially, opening up new possibilities for space exploration and asteroid utilization. Ultimately, ultra-fast rotators remind us that the universe is still full of surprises. Just when we think we understand the rules, we discover something that forces us to rethink everything. These asteroids push the limits of what we know about physics, celestial mechanics, and even the history of the solar system itself. And as we continue to explore, who knows what other mysteries we will uncover? Ultra-rapidly spinning asteroids may hold answers to some of the biggest questions about the early solar system, but studying them is incredibly difficult. Because of their extreme spin, any spacecraft attempting to approach one faces significant challenges. The high rotation speeds make it nearly impossible for a probe to land safely without being thrown off by the centrifugal forces. Even getting close enough to collect data is a challenge, as loose material on the asteroid's surface may be flung outward at high velocities. Despite these obstacles, astronomers are developing ways to study these objects more effectively. One approach is to use radar observations, which allows scientists to determine an asteroid's shape, size, and rotation rate without needing to send a spacecraft. By bouncing radio waves off an asteroid and analyzing the returning signals, researchers can construct detailed 3D models of its structure. This technique has already been used to study several ultra-fast rotators, providing valuable insights into their physical properties. Another method involves studying how these asteroids reflect sunlight. By measuring changes in brightness over time, scientists can determine their spin rates and even infer details about their surface composition. If an asteroid's brightness fluctuates in a predictable pattern, it suggests a regular rotation. But if the brightness changes unpredictably, it could indicate an irregular shape, a chaotic rotation, or the presence of loose material being ejected due to extreme spin. One of the most fascinating possibilities is that some ultra-rapidly spinning asteroids could be breaking apart in real time. If an asteroid is rotating faster than its structural integrity allows, it may begin to shed material gradually, creating a stream of debris that follows its orbit. In some cases, this could explain why we see asteroid pairs, two objects traveling together through space. Scientists believe that at least some of these asteroid pairs formed when a single ultra-fast rotator spun itself apart, splitting into two separate bodies. This raises another intriguing question: could some of these asteroids eventually break apart entirely, creating small, temporary rings around themselves? While rings are typically associated with large planets like Saturn, some studies suggest that small asteroids could temporarily develop ring-like structures if they eject enough material due to rapid rotation. These rings would not be permanent, as the debris would eventually drift away, but their existence would challenge our understanding of how material behaves in microgravity environments. The possibility of asteroid rings ties into a broader mystery about the stability of ultra-fast rotators. If an asteroid is spinning at extreme speeds, why doesn't it lose mass more often? One hypothesis is that some of these objects have a type of cohesive strength that allows them to remain intact even when spinning at near-destructive speeds. Instead of being held together by gravity alone, they may have a form of electrostatic cohesion, where tiny particles on the surface are bound together by weak electrostatic forces. This idea is supported by observations of certain small asteroids that appear to have a layer of fine dust clinging to their surfaces despite the lack of strong gravity. If ultra-fast rotators have a similar mechanism at work, it could explain why they can survive such high spin rates without shedding material constantly. There is also the question of how these asteroids acquired their extreme spin in the first place. While the YORP effect plays a significant role, it may not be the only factor. Some scientists speculate that high-speed collisions in the past could have set these objects spinning at incredible rates. If an asteroid was struck by another object at just the right angle, it could impart enough rotational energy to turn it into an ultra-fast rotator. If this is the case, then some ultra-fast rotators might be relatively young in cosmic terms. Instead of being billions of years old, they could have formed much more recently due to impacts within the asteroid belt. This would suggest that the population of ultra-rapidly spinning asteroids is constantly changing, with new ones forming as old ones either slow down or break apart. Another fascinating aspect of ultra-fast rotators is their potential to provide insight into planetary defense strategies. If an asteroid were on a collision course with Earth, one possible way to deflect it would be to alter its spin rate. By increasing or decreasing an asteroid's rotation, scientists could theoretically change its trajectory over time, steering it away from a potential impact. However, ultra-fast rotators complicate this strategy. Because these objects are already spinning at such extreme rates, attempting to manipulate their rotation could have unpredictable effects. Instead of deflecting them, we might accidentally cause them to break apart, creating multiple smaller fragments that could still pose a threat. Understanding how ultra-fast rotators behave under different forces is therefore critical for developing effective planetary defense techniques. One of the biggest unknowns is whether ultra-fast rotators exist in other star systems. So far, our observations are limited to the solar system, but with the increasing number of exoplanet discoveries, it is only a matter of time before we begin detecting asteroid belts around other stars. If ultra-fast rotators exist elsewhere, they could provide valuable clues about how planetary systems form and evolve beyond our own. As telescope technology continues to improve, astronomers will likely discover even more ultra-rapidly spinning asteroids, some of which may challenge our current understanding of physics. Future space missions equipped with advanced sensors and possibly even robotic landers could finally provide direct measurements of their internal structure, revealing whether they are solid monoliths, metallic cores, or something entirely unexpected. The study of ultra-fast rotators is still in its infancy, but it is already reshaping our understanding of asteroids and their role in the solar system. These objects push the limits of what we thought was possible, challenging our models of how small celestial bodies behave under extreme conditions. As we continue to explore the cosmos, these rapidly spinning asteroids will remain one of the most intriguing and mysterious classes of objects we have ever encountered. Ultra-rapidly spinning asteroids are like nature's ultimate physics experiment, constantly testing the limits of what small celestial bodies can endure. Their extreme rotation speeds stretch our understanding of how these objects remain intact, how they evolve over time, and what forces are truly at play in the depths of space. One of the most perplexing aspects of these asteroids is their ability to withstand rotational forces that should, by all logic, tear them apart. Most asteroids, especially the small ones, are not solid monoliths. Instead, they are often rubble piles, collections of loosely bound rocks held together by gravity, and, in some cases, weak cohesive forces. If a rubble pile asteroid were to spin too fast, the centrifugal force would overcome the weak gravitational bonds, causing the material to fly outward. This is why astronomers initially believed there was a natural limit to how fast an asteroid could rotate. However, ultra-fast rotators defy this expectation. They spin so quickly that their equatorial regions should be experiencing forces stronger than their own gravity. If they were rubble piles, they should have long since disintegrated. The fact that they haven't suggests two possibilities: either they are not rubble piles at all, but rather solid rock formations, or there is some unknown force holding them together. Some scientists believe that electrostatic forces might play a crucial role. In microgravity environments, small particles can develop electrical charges, causing them to stick together in unexpected ways. If ultrafast rotators have a significant amount of electrostatically bound material, it could explain why they maintain their structure despite extreme spin rates. This theory is still being tested, but if proven, it could revolutionize our understanding of how small bodies behave in space. There is also the possibility that some of these asteroids are composed of highly cohesive material, such as metal-rich compositions that resist breaking apart. Certain iron-nickel asteroids, for example, are thought to be the remnants of the cores of ancient protoplanets. If an ultrafast rotator is made of solid metal, it could theoretically withstand rotation speeds that would destroy a more loosely bound body. The study of ultrafast rotators also has implications for asteroid mining. Future space missions may seek to extract valuable materials from asteroids, but if these objects are spinning at extreme rates, landing on them, or even matching their speed could prove incredibly difficult. Engineers will need to develop advanced techniques for stabilizing spacecraft near these fast-moving bodies. Understanding their structure and composition will be key to making asteroid mining a viable industry. Beyond mining, ultrafast rotators could also provide clues about the early solar system. Some scientists suspect that the most rapidly spinning asteroids may be remnants of violent collisions that took place billions of years ago. If an asteroid was shattered in a high-speed impact, the resulting fragments might retain a rapid spin as they reassembled. By studying the rotational properties of these objects, astronomers may be able to reconstruct their history and gain insight into the chaotic conditions of the early solar system. Another intriguing aspect of ultrafast rotators is their potential role in planetary defense. If one of these objects were to be on a collision course with Earth, standard deflection techniques might not work. Many proposed asteroid deflection strategies, such as kinetic impactors or gravity tractors, rely on predictable asteroid behavior. But an ultra-fast rotator could react unpredictably to an attempted deflection, potentially fragmenting into multiple hazardous pieces instead of simply changing course. This makes understanding these asteroids a matter of practical importance, not just scientific curiosity. If we ever face a real asteroid impact threat, knowing how these extreme rotators behave could be the difference between success and disaster. Researchers are already exploring potential ways to slow down or stabilize these objects, but much more work needs to be done before we can confidently alter their trajectories. The YORP effect, one of the primary drivers of ultra-fast rotation, remains a topic of ongoing study. As sunlight strikes an asteroid, it exerts a tiny amount of pressure. Over millions of years, this pressure can gradually accelerate an asteroid's spin. However, not all asteroids respond to the YORP effect in the same way. Some may reach a stable rotation rate, while others continue accelerating until they reach the limits of structural stability. Scientists have even observed cases where the YORP effect has caused asteroids to change shape. As they spin faster, they may become elongated or develop equatorial bulges. In extreme cases, material can be ejected from the surface, forming a trail of debris or even leading to the formation of small moons. Some of these moons may eventually drift away, while others may be reabsorbed by the parent asteroid over time. Observations of asteroid pairs, two asteroids traveling together in close proximity, suggest that many of these objects were once single bodies that split due to excessive spin. This phenomenon may be more common than previously thought, meaning that many asteroids in our solar system could be the remnants of past ultra-fast rotators that failed to hold themselves together. Future space missions will play a crucial role in uncovering more details about these enigmatic objects. Missions like NASA's OSIRIS-RX and Japan's Hayabusa 2 have already demonstrated the ability to study asteroids up close and even return samples to Earth. A dedicated mission to an ultra-fast rotator could provide unprecedented insights into their structure, composition, and evolutionary history. As we continue to study these mysterious celestial bodies, we may find that they hold answers to some of the biggest questions about the formation of the solar system, the behavior of small bodies in space, and even the potential for asteroid-based resources. The more we learn, the more we realize just how much remains unknown. Ultra-rapidly spinning asteroids challenge our expectations and push the boundaries of our understanding. Whether they are remnants of ancient collisions, test cases for planetary defense, or potential goldmines for future space industries, they are far more than just spinning rocks in space. They are puzzles waiting to be solved, mysteries waiting to be unraveled, and possibly, keys to unlocking the secrets of the universe itself. Ultra-rapidly spinning asteroids aren't just an oddity. They're a direct challenge to our understanding of how small celestial bodies hold themselves together. Their extreme rotational speeds defy conventional physics, suggesting there are forces at work that we still don't fully grasp. When we first started detecting asteroids that were spinning so fast they should have broken apart, scientists had to question everything they thought they knew about these objects. One of the biggest mysteries is how some asteroids manage to stay intact despite rotation rates that should be pulling them apart. If a small asteroid is made of loosely packed material, what scientists call a rubble pile, then it should have a natural limit to its spin speed. If it rotates too fast, the weak gravitational bonds holding it together should fail, and chunks of rock should start flying off into space. But ultra-fast rotators don't seem to follow this rule. Instead, they spin at speeds that should have already shattered them. This raises an obvious question. Are these asteroids somehow different from the rubble piles we're used to? One possibility is that ultra-fast rotators are made of solid rock rather than loose material. If an asteroid is a single, monolithic chunk of rock, then it can withstand much higher spin rates than a collection of loose debris. But even solid rock has its limits. If the rotational force at the surface is greater than the asteroid's own gravity, then pieces of it should still start breaking away. The fact that this doesn't always happen suggests that something else might be reinforcing these asteroids. Electrostatic forces could be a key piece of the puzzle. In microgravity environments, dust and small particles can develop static charges, which cause them to cling together in unexpected ways. If an ultrafast rotator has a significant amount of electrically charged material, It might help bind the surface together even when gravity alone isn't strong enough. Some researchers believe that this could explain why these asteroids don't fly apart despite their extreme rotation rates. Another possible explanation is that ultra-fast rotators are unusually strong because of their composition. Some asteroids are believed to be rich in metal, particularly nickel and iron, which could make them much more resistant to breaking apart under rapid rotation. These metal-rich asteroids might have originated from the shattered cores of ancient protoplanets, which means they could be among the most ancient relics of the early solar system. If an asteroid is mostly metallic, it could behave very differently from a typical rubble pile, holding together even at speeds that should be impossible. Studying these fast-spinning asteroids isn't just about solving a cosmic mystery, it has real-world implications. If humans ever want to mine asteroids for valuable resources, ultra-fast rotators could pose a significant challenge. A spacecraft attempting to land on one of these asteroids would have to deal with extreme surface speeds, making it difficult to anchor or collect material. Understanding how these objects behave could help engineers design better space mining technology in the future. There's also the issue of planetary defense. If an asteroid on a collision course with Earth were spinning at an ultra-fast rate, it could react unpredictably to deflection attempts. Many proposed asteroid deflection strategies assume that the target is relatively stable, but if an ultra-fast rotator were struck by a kinetic impactor, it could fragment into multiple smaller pieces instead of simply changing course. This could make it even more dangerous, as we would then have to deal with several incoming threats instead of just one. Scientists are also interested in how ultra-fast rotators might evolve over time. The YORP effect, caused by the way sunlight exerts pressure on an asteroid's surface, can gradually speed up an asteroid's spin over millions of years. This means that some asteroids might not have started out as ultra-fast rotators, but instead developed their extreme spin rates over time. Eventually, some of them might reach a breaking point where they can't hold themselves together any longer, splitting apart into smaller pieces. There's evidence that this has already happened in some cases. Astronomers have observed asteroid pairs, two asteroids orbiting close together, that appear to have once been a single body. The most likely explanation is that the original asteroid spun so fast that it couldn't stay intact, leading to a split. This suggests that ultra-fast rotators could be responsible for creating new asteroids through rotational breakup. Future space missions could provide even more answers. NASA's OSIRIS-REx mission and Japan's Hayabusa 2 mission have already demonstrated that we can study asteroids up close and even return samples to Earth. A dedicated mission to an ultra-fast rotator could help scientists determine exactly what these objects are made of, how they maintain their structure, and whether electrostatic forces or unusual compositions are keeping them together. The more we learn about these spinning asteroids, the more we realize just how much remains unknown. They could be relics from the early solar system, evidence of past collisions, or even test cases for understanding planetary defense strategies. But one thing is certain: ultra-fast rotators are some of the strangest and most fascinating objects in our cosmic neighborhood, and they're challenging everything we thought we knew about how asteroids behave. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.